Hey everybody, welcome back to my channel. This is WireDogSec, back with another video for you guys. Today's video, we are going to go over this room in TryHackMe, Intro to Containerization, learn about the technologies and benefits of containerization. Now, this is a part of this module here, Container Security. Learn how containerization works, its benefits, potential vulnerabilities, and the steps necessary to secure your container. Containerization technologies such as Docker are popular for developing and deploying applications. In this module, you will learn how Docker works, some common vulnerabilities, and various measures that can be taken to secure your container from attack. All right, so this is the first room, Intro to Containerization. Next one is Intro to Docker. So I got a little ahead of myself here, and this one's already uploaded, so go ahead and check that out. We have Intro to Kubernetes and Container Vulnerabilities, and also this Container Hardening. So we're gonna go through all these modules here. Now, you may be watching these videos separately or all together in one whole video. Either or, you'll get the same material. So let's flip back over here to our Intro to Containerization. Take a look here. Learning outcomes. By completing this room, you will know what containerization is and what containers are, where and why containerization is used, a fundamental understanding of the popular containerization technology called Docker, what makes Docker so popular, how containerization works. With that said, complete the question below and progress on to the next task. So we are done with this, but before we get ahead of ourselves, be sure to like, comment, share, subscribe, hit that notification bell if you want to help support the channel. Without further delay, let's go ahead and dive into it. Task 2. What is containerization? In computing terms, containerization is the process of packaging an application and the necessary resources, such as libraries and packages, required into one package named a container. The process of packaging applications together makes applications considerably portable and hassle-free to run. Modern applications are often complex and usually depend on frameworks and libraries being installed on a device before the application can run. These dependencies can be difficult to install depending on the environment that application is running. Some operating systems might not even support them. Create difficulty for developers to diagnose and replicate faults, as it could be a problem with the application's environment, not the application itself. Can often conflict with each other. For example, having multiple versions of Python to run different applications is a headache for the user, and an application may work with one version of Python and not another. Containerization platforms remove this headache by packaging the dependencies together and isolating. Note, this is not to be confused with security isolation in this context, the application's environment, okay? If the device supports the containerization engine, a user will be able to run the application and have the same behavior. So here's a diagram here, a diagram demonstrating 3 containers on a single computer. So you have container 1, 2, and 3, application 1, environment, and it's the same across the board here. You have the Docker engine, you have the computer operating system, the host, and you have the physical computer there. In the screenshot above, we can see how 3 applications and their environments, such as dependencies, are packaged together and do not directly interact with the physical computer, but rather the containerization engine. In this case, it is Docker. We will come on to discuss precisely how containers isolate from one another, but for now, it's important to understand that the isolation is a core feature of containers. However, it is worth noting that containerization platforms make use of the namespace feature of the kernel, which is a feature used so that processes can access resources of the operating system without being able to interact with other processes. The isolation offered by namespaces adds a benefit of security because it means that if an application in the container is compromised, usually other containers are unaffected here, and it says unless they share the same namespace. Okay, so take that into consideration there. Alternatives such as virtual machines will require a whole operating system being installed to run the application, taking up large amounts of disk space and other computing resources such as CPU and RAM, and that's absolutely true. Okay, we have a couple questions here. Let's see here. What is the name of the kernel feature that allows for processes to use resources of the operating system without being able to interact with other processes? And this is going to be namespace. As we can see up here, platforms make use of the namespace feature of the kernel. Next one, in a normal configuration, can other containers interact with each other? Well, that's going to be no, because you can see that they are isolated from each other, right? Let's go ahead and continue on here. Task number 3, introducing Docker. I'll promise I'll try to keep the sales pitch relatively short. Docker is a relatively hassle-free, extensive, and open-source containerization platform. The Docker ecosystem allows applications, images will come into this in a later room, to be deployed, managed, and shared with ease. Working on Linux, Windows, and Mac OS, Docker is a smart choice for running applications. Applications can be published as images and shared with others. All that is required is pulling or downloading the image and running it with Docker. Docker employs the same technology used in containerization to isolate applications into containers called the Docker engine. The Docker engine is essentially an API that runs on the host operating system, which communicates between the operating system and containers to access the system's hardware, such as CPU, RAM, networking, and disk. Because of this, Docker engine is extensive and allows you to do things like, number one, connect containers together. For example, a container running a web application and another container using a database. Number two, export and import applications images. Three, transfer files between the operating system and container. Docker uses the programming syntax YAML to allow developers to instruct how a container should be built and what is run. This is a significant reason why Docker is so portable and easy to debug. Share the instructions and it will build and run the same on any device that supports the Docker engine suite. The Docker engine allows containers to be orchestrated, meaning that multiple containers can be built as part of a group, allowing containers to communicate with each other. For example, one container running a web server and another container running a database can communicate. We will come onto this feature in a later room. We have some questions here. What does an application become when it's published using Docker? And it has X's here. Fill in the X's. Okay. So that should be, I think it's an image for this one. What is the abbreviation of the programming syntax language that Docker uses? And that's YAML. I think that stands for yet another markup language, if I'm not mistaken. Task number 4, the history of Docker. Originally created by Solomon Hykes in 2013, Docker is an open source and has become a well-renowned name within containerization. Docker started as an internal project for .cloud, a PaaS provider, where it was then showcased in PyCon in 2013 and then quickly made open source. While containerization's original concept started in 1979 with Unix v7, Docker has made containerization a popular technology since its release in 2013. Docker's popularity is due to making the benefits of containerization accessible and modern. As of April 2022, it is fair to say that Docker is extremely popular. To be precise, 13 million developers are using Docker. There are 7 million applications made and ready to use with Docker. 13 billion applications are downloaded monthly, and this is just from the official repository. So there's dockerhub.com, there's docker.com if you want to check out those sources there. Okay, we have some questions here. And what year was Docker originally created? Well, that's going to be 2013 because they did it at PyCon, right? Where was Docker first showcased? And that's going to be PyCon, as I just said. Okay. What version of Unix had the first concepts of containerization? That's going to be version 7. So V7 for this one here. Okay. Next one, task number 5, the benefits and features of Docker. If it hasn't been said enough, here is another attempt. Docker is an agile, convenient, and extensive means of deploying an application. Let's explore this in detail in the headings below. Docker is free. The Docker ecosystem is free to use and open source. While business plans exist, you can completely download, use, create, run, and share images. Docker is compatible. The Docker platform is compatible with Linux, Mac OS, and Windows. Because of how containerization works, if a device supports the Docker engine, you can run any container regardless of the application or dependencies. Docker is efficient and minimal. Docker is an efficient way to isolate applications in comparison to alternatives such as virtual machines. This is because the Docker engine runs and interacts with the host operating system, and the containers do not run a fully fledged operating system for each container. For example, containers can share a minimal operating system image, meaning you only need to store it once. A minimal Ubuntu image is 100 megabytes, which can be stored once and used multiple times. Compare this to the Ubuntu server image, about 1 gigabyte after a fresh install per VM. So here's an example here, inspecting the size of the Ubuntu Docker image. So they did Docker image ls to list those out here. You have Ubuntu tag latest, there's image ID created 4 weeks ago, and then there's the size of it. Docker is easy to get started with. The Docker developer documentation is very well documented with lots of articles, working examples, and answers questions on the internet. The chances are, if you want to do something in Docker, someone has already asked about it or done it. The syntax to get started with Docker is easy to pick up. You can start your first container in no time. The fact that there are Docker images for all sorts of applications already published helps. Docker is easy to share with others. A significant benefit of Docker is its portability. Docker uses images to store instructions to dictate how the container should be built, just an instruction manual. These images can be exported, shared, and uploaded to both public and private repositories such as Docker Hub and GitHub. The image can be run by anything that supports the Docker image or engine as long as the syntax is valid. Docker is minimal. These Docker images discussed above are minimal. You will often find many core and luxurious tools and packages in a container that are missing. While this can look like a disadvantage, it is in fact allows containers to be built exactly how the developer wishes. Better security, knowing exactly what runs within a container, can reduce the risk of unnecessary packages becoming vulnerable and posing a security risk. Docker is cheaper to run. Running containers is usually a cheaper option than running virtual machines. This is especially noticeable in cloud environments where CPU, RAM, and disk space are expensive. For example, you can quite happily run a few containers on a single $5 cloud provider VPS, whereas you will not be able to run a virtual machine. This is due to the fact that running virtual machines requires hardware that supports virtualization, which is only found on costly tiers of a cloud provider, if at all. Virtual machines require lots of memory and disk space as you are running a separate operating system on top of the physical machine. So README, we read through everything here. Now we can see what Docker has to offer, some of the capabilities, and how it can benefit you. Task number 6, how does containerization work? Namespaces essentially segregate system resources such as processes, files, and memory away from other namespaces. Every process running on Linux will be assigned two things: a namespace, a process identifier, which is the PID. Namespaces are how containerization is achieved. Processes can only see other processes that are in the same namespace. No conflicts in theory. Take Docker, for example. Every new container will be running as a new namespace, although the container may be running multiple applications and in turn processes. Let's prove the concept of containerization by comparing the number of processes there are in a Docker container that is running a web server versus the host operating system at the time here. So you want to take a look at the screenshot real quick and you can examine what they're talking about here. So we got Docker build up here, talking about opt Google Chrome stuff over here. Okay, good to know there. Put simply, the process with an ID of 0 is the process that is started when the system boots. Process numbers increment and must be started by another process, so naturally the next process ID will be number 1. This process is the system in it. For example, the latest versions of Ubuntu use systemd. Any other process that runs will be controlled by systemd, process number 1. We can use the process number 1's namespace on an operating system to escalate our privileges. Whilst containers are designed to use these namespaces to isolate from each other, they can instead coincide with the host computer's processes. This gives us a nice opportunity to escape. That's interesting there. Okay. What command can we use to view a list of running processes? Okay, and we already have it there, the PS and then AUX for that. All right, so we should be good to go there. Now we're going to get into the practical side of things with task number 7 here. Deploy the static site attached to this task. Containerize the applications to reveal the flag. Containerize the application in the static site. What is the flag? So view site here. And now let's go ahead and try this. Go ahead and try this yourself and then come back to the video and then we will step through it together. Good luck. Hey everybody, this is WireDogSec. Just a quick reminder to subscribe to the channel and hit the notification bell. Once you hit the notification bell, be sure to set to all notifications so you know every time I post to the channel, upload a video, all that good stuff. Let's continue to grow our glorious community here. We are in the cyber trenches. We're not just reporting on it. Be sure to check out my channel as well. I have tons of videos. You can see here over 300 videos ready for you to check out and learn something from. Be sure to review my posts. I'm frequently posting new things to my channel here, including jobs and everything related to that. Also, I have tons of playlists here that you can review, make it more convenient for you. Anyway, happy defending, happy hacking, enjoy the video. All right, let's take a look here. Now, we just have to put this in order, it looks like. Assemble the layers of the container to retrieve the flag. And the discussed this in one of these tasks here. So if we just go ahead and locate that, maybe it was the first one. Let's see here. Nope, not that one. I think we already checked this here. There we go. So we're just going to follow this diagram basically. So physical machine's already there, and now we need the computer operating system, which is the host. So let's do this here, physical OS, and then we have the container engine, and then on top of that we have the container OS, I guess, and then application. There we go. So now we're done. Easy peasy. So hopefully y'all have learned something in here about these containers and whatnot. I've used Docker before, but not extensively like a developer would use. I've set up images before in like a lab environment and whatnot. You'll probably come across this as well throughout your career as you're doing these labs. But we are pretty much done here. Okay, and remember to check out the next video, which is going to be Intro to Docker. So check that out. It should already be uploaded to the channel. But anyway, let's go ahead and close out this video and wrap it up. Okay, we're done. If you want to help support the channel, be sure to like, comment, share, subscribe, and hit that notification bell so you know every time I upload to the channel. As always, thank you all for taking the time to watch my video. I appreciate y'all's continued support. Have a nice day, and I will see you in the next one. Happy hacking and happy defending. Hey everybody, this is WireDogSec. Just a quick reminder to subscribe to the channel and hit the notification bell. Once you hit the notification bell, be sure to set to all notifications so you know every time I post to the channel, upload a video, all that good stuff. Let's continue to grow our glorious community here. We are in the cyber trenches. We're not just reporting on it. Be sure to check out my channel as well. I have tons of videos that you can see here, over 300 videos ready for you to check out and learn something from. Be sure to review my posts. I'm frequently posting new things to my channel here, including jobs and everything related to that. Also, I have tons of playlists here that you can review, make it more convenient for you. Anyway, happy defending, happy hacking, enjoy the video. Hey everybody, welcome back to my channel. This is WireDogSec, back with another video for you guys. Today's video, we are in TryHackMe. This is the Intro to Docker room. Learn to create, build, and deploy Docker containers. Now, we're going to take a look at this room here before we dive into the Container Vulnerabilities room here. That's going to be the next video, perhaps, and I may even combine these two videos together eventually, because I know some of y'all like to view that. But before we get into the container vulnerabilities about Docker, it says that the prerequisites would be this Intro to Docker room. So that's where we are going to start here. Okay, so let's go ahead and take a look at this room here for Intro to Docker. Scroll all the way down here to task number 7, practical, and go ahead and start up this machine here. As you can see, it's already running for me. And let's take a look at this task 1 introduction. In this room, you'll get your first hands-on experience deploying and interacting with Docker containers. Namely, by the end of the room, you will be familiar with the following: the basic syntax to get you started with Docker, running and deploying your first Docker container, understanding how Docker containers are distributed using images, creating your own image using a Dockerfile, how Dockerfiles are used to build containers, using Docker Compose to orchestrate multiple containers, applying the knowledge gained from the room into the practical element at the end. Please note, it is strongly recommended that you are at least familiar with basic Linux syntax, such as running commands, moving files, and familiarity with how the file system structure looks. If you have completed the Linux fundamental module, you will be all set for this room, or you can check out my channel for anything related to Linux, okay? Additionally, it is important to remember that you will need internet connectivity to pull Docker images. If you are a free user and wish to practice the commands in this room, you will need to do this in your own environment. Okay, complete this question before progressing to the next task. Now, if you want to help support the channel, be sure to like, comment, share, subscribe, and hit that notification bell so you know every time I upload to the channel. Without further delay, let's go ahead and dive into it. Task 2, basic Docker syntax. Docker can seem overwhelming at first. However, the commands are pretty intuitive, and with the bit of patience, you'll be a Docker wizard in no time. The syntax for Docker can be categorized into 4 main groups: running a container, managing and inspecting containers, managing Docker images, Docker daemon stats, and information. We will break down each of these categories in this task. Managing Docker images, Docker pool. Before we can run a Docker container, we will first need an image. Recall from the intro to containerization room that images are instructions for what a container should execute. There's no use running a container that does nothing. Interesting. So maybe I'll check out this room as well at some point. In this room, we will use the Nginx image to run a web server within a container. Before downloading the image, let's break down the commands and syntax required to download an image. Images can be downloaded using the docker pull command and providing the name of the image. For example, docker pull nginx. Docker must know where to get this image, such as from a repository, which we'll come onto in a later task. Continuing with our example above, let's download the Nginx image. Please note this command will not work on the practical machine attached to this room, as internet access is required. So I guess you can do this on your own VM if you want to go that route. Obviously, it's not going to work because there's no internet connectivity. So if you were to do that, you do docker pull nginx, and it's going to pull that information or pull that down here, right? Download it, newer image for nginx, latest, etc. By running this command, we are downloading the latest version of the image titled Nginx. Images have these labels called tags, and these tags are used to refer to variations of an image. For example, an image can have the same name but different tags to indicate a different version. I've provided an example of how tags are used within the table. So we have docker image tag, command example, and explanation. Ubuntu. Latest, docker pull Ubuntu is the same as docker pull Ubuntu :latest. Explanation: this command will pull the latest version of the Ubuntu image. If no tag is specified, Docker will assume you want the latest version if no tag is specified. And it says, it is worth remembering that you do not always want the latest. This image is quite literally the latest in the sense it will have the most recent changes. This could either fix or break your container. And you have the other ones here. So you have Ubuntu 22.04, docker pull Ubuntu, and then have the version 22.0. This command will pull version 22.04 jammy of the Ubuntu image, and it looks pretty straightforward. Okay, so they're specifying the version that they want to pull down here. So the next one's going to be version 20.04, then 18.04. Okay, so I think we get the gist of that. When specifying a tag, you must include a colon between the image name and tag. For example, Ubuntu tag or colon 22.04, so image, and then colon, then the tag is going to be that other item here, so the version or tag right there. Okay, don't forget about tags. We will return to these in a future task. Docker image xyz. The docker image command with the appropriate option allows us to manage the images on our local system. To list the available options, you can simply do docker image to see what we can do. I've done this for you in the terminal below. So if we were to do that here, I'm just going to see if this actually works over here, if I can spell correctly. All right, so let's go ahead and paste that in and see. All right, so there we go. So we have similar output here, and it tells you the different commands available here. So you have build, history, import, inspect, load, ls, etc., etc. Okay, so that's good stuff to know there. It tells you some other syntax here. In this room, we are only going to cover the following options for Docker images. Pull. We have done this above. ls, list images. rm, remove an image. Build. We will come onto this in the building your first container task. Docker image ls. This command allows us to list all images stored on local system. We can use this command to verify if an image has been downloaded correctly and to view a little bit more information about it, such as the tag, when the image was created, and the size of the image. All right, so it looks something like this. So let's go ahead and just copy and paste this over. All right, there we go. For example, in the terminal above, we can see some information of for the 2 images on the system. So repository tag image ID created inside. So Ubuntu tag 22.04. There's the image ID created 10 days ago, and then there's the size. And we have something similar over here, created 3 years ago, etc., etc. Okay. Docker image rm. If we want to remove an image from the system, we can use docker image rm along with the name or image ID. In the following example, I will remove the Ubuntu image with the tag 22.04. My command will be docker image remove Ubuntu :22.04 for the tag. It is important to remember to include the tag with the image name. Yes, of course. Okay, so it seems pretty straightforward. If we were to run a docker image ls, we would see that the image is no longer listed. Okay, as you can see, it's been removed. So that's good to know. Questions. If we wanted to pull a Docker image, what would our command look like? Okay, so that would be Docker, right? And that would be Docker. So if we want to pull it down, let me go look at the commands again. I'm pretty sure I know what it is, but I just want to, yeah, it's going to be pull. So let's go ahead and type that in there. Okay, next one, if we wanted to list all images on a device running Docker, what would our command look like? Okay, so that's going to be Docker and then image and ls to list that. Let's say we wanted to pull the image TryHackMe, no quotations. What would our command look like? So that would be Docker, of course, and then Docker pull, and then it'll be TryHackMe. Let's say we want to pull the image TryHackMe with the tag 1337 or leet, no quotations. What would our command look like? So it's going to look like the one up above, except a little bit different here. So Docker and then pull TryHackMe, and then we have that colon there, and then we have to specify the tag, okay, and that's going to be 1337 for that. And we're done with that. Sweet. So let's go ahead and continue on to task number 3 here, and we're going to talk about running your first container. The Docker run command creates running images or containers from images. This is where commands from the Dockerfile as well as our own input at runtime are run. Because of this, it must be some of the first syntaxes you learn. The command works in the following way. So you have Docker run, you have options, image name, commands, arguments. The options enclosed in brackets are not required for the container to run. Docker containers can be run with various options depending on how we will use the container. This task will explain some of the most common options that you may want to use. First, simply running a container. Let's recall the syntax required to run a Docker container, which is this here. So Docker run options, image name, command, and arguments. In the example, I'm going to configure the container to run the following: an image named hello world interactively by providing the -it switch in the options command. This will allow us to interact with the command or container directly. I'm going to spawn a shell within the container by providing the /bin/bash as the command part. This argument is where you will place what commands you want to run within the container, such as a file, application, or shell. So to achieve the above, my command will look like the following. So Docker run -it, hello world, and then bin bash. All right, and here is what it looks like in the terminal. For interactive mode, we can verify that we have successfully launched a shell because our prompt will change to another user account and hostname. The hostname of a container is the container ID, which can be found using the Docker PS. For example, in the terminal above, our username and hostname are root at, and then whatever that is there, okay? Running containers. So if we want to do that, Docker, and then PS, there we go, here, okay. Running containers continued. As previously mentioned, Docker containers can be run with various options. The purpose of the container and the instructions set in a Docker file will come onto this in a later task. It determines what options we need to run the container with. To start, I've put some of the most common options you may need to run the Docker container into the table. So you have option, explanation, and then relevant Docker file instruction. And there's the example. So -d, this argument tells the container to start in detached mode. This means that the container will run in the background. And then here's an example of what that looks like here. So Docker run -d, hello world, -it. We know that's going to be that interactive mode, right? So this argument has two parts. The I means run interactively, and the T tells Docker to run a shell within the container. We would use this option if we wish to interact with the container directly once it runs, and here's how to do that here: Docker run -it, and then hello world, or that name there for it, right? -v, this argument is short for volume and tells Docker to mount a directory or file from the host operating system to a location within the container. The location these files get stored is defined in the Docker file. So that's good to know there. And this is volume, and then Docker run -v, and there's the location here, host OS directory, and then contain hello world -p. Okay, there's quite a few other ones here. So this argument tells Docker to bind a port the host operating system to a port that is being exposed to the container. You would use this instruction if you are running an application or service such as a web server in the container and wish to access the application or service by navigating to IP address. Okay, so expose docker run -p and then 8080 and then web server is what that says there, I believe. And let me just minimize this real quick. Okay. Next one is --rm. This argument tells Docker to remove the container once the container finishes running whatever it has been instructed to do. And Docker run --rm hello world --name. The argument lets us give a friendly, memorable name to the container. When a container is run without this option, the name is 2 random words. We can use this. I guess, option to name a container after the application. The container is running. Okay, so Docker and then run --name hello world. Good to know there. These are just some arguments we can provide when running a container. Again, the most arguments we need to run will be determined by how the container is built. However, arguments such as --rm and --name will instruct Docker on how to run the container. Other arguments include, but are not limited to, the following: telling Docker what network adapter the container should use, what capabilities the container should have access to. This is covered in the Docker rodeo room on TryHackMe. Interesting. Storing a value into an environment variable. If you wish to explore more of these arguments, I highly suggest reading the Docker run documentation there, so feel free to check that out if you're interested. Listing running containers. To list running containers, we can use the Docker ps command. This command will list containers that are currently running, like so, which we just saw that there earlier. Okay, so that's good to know there. And this command will also show information about the container, including the following. So let's go ahead and take a look at that here and see what it says. So the container's ID, what command is the container running, when was the container created, how long has the container been running, what ports are mapped, the name of the container. To list all containers, even stopped, you can use Docker ps-a. So that's good to know here. So there's a lot of helpful information here about Docker that we could utilize, right? So here's an example of that here, and there's the output. So that's good to know there. So we got some more questions here. Let's take a look. What would our command look like if we wanted to run a container interactively? So that would be, of course, Docker, if I can spell Docker. And remember, you had to use that -it for it. So there it is right here. So run and then -it should be what we're looking for here. There we go. What would our command look like if we want to run a Docker container in detached mode? I believe that was the -d option up here. Yes, so we're going to go ahead and copy and paste this down below for our answer there. Let's say we want to run a container that will run and bind a web server on port 80. What would our command look like? Assume we are not specifying any image here. Okay, so if we want to do that on ports, if we go back up here, it talks about this here. So this looks like what we need. So let's go ahead and plug this in. How would we list all running containers? And that should be the Docker. And this is going to be Docker ps to list all running containers. Last one here. Now, how would we list all containers, including stopped ones? So if you scroll back up here, it should be this one here, this -a option, right? So let's go ahead and put that in there. Task number 4, intro to Dockerfiles. Dockerfiles play an essential role in Docker. Dockerfiles is a formatted text file which essentially serves as an instruction manual for what containers should do and ultimately assembles a Docker image. Use Dockerfiles to contain the commands the Docker or the container should execute when it is built. To get started with Dockerfiles, we need to know some basic syntax and instructions. Dockerfiles are formatted in the following way. So instruction and argument. First, let's cover some essential instructions. So you have instruction, description, and example here. From the instruction sets a build stage for the container as well as setting the base image, operating system. All Docker files must start with this, and then it says from Ubuntu for the example, run. This instruction will execute commands in the container within a new layer. So run, who am I? It's going to run that command. Copy. This instruction copies files from the local system to the working directory in the container. The syntax is similar to the cp command. Copy, home, semantic, my folder, app, work, dir. Or work directory, I guess. This instruction sets the working directory of the container similar to using cd on Linux. So work dir and then sets to the root of the file system, the container, cmd. This instruction determines what command is run when the container starts. You should use this to start a service or application. So cmd bin sh-c script.sh expose. This instruction is used to tell the person who runs the container what port they should publish when running the container. Expose 80. This tells the person running the container to publish to port 80. So there's an example here, docker run -p 8080, and we saw that earlier. Now that we understand the core instructions that make up a Docker file, let's see a working example of a Docker file. But first, I'll explain what I want the container to do. So number one, use the Ubuntu version 22.04 operating system as the base. Number two, set the working directory to the root of the container. Number three, create the text file hello world.txt. Interesting there. All right, so this is a comment. Use Ubuntu 22.04 as the base operating system of the container, and to do that, you're going to use that from Ubuntu 22.04. So remember back to tags to get that version of it. Set the working directory to the root of the container. So workdir, and it's setting it to the root, which is that /. Create hello world.txt. They're using run touch hello world.txt. Remember, so run, you can run those commands on it, and they're using touch to create that file hello world.txt, okay, that you would normally see in like a terminal. Remember, the commands that you run via the run instruction will depend on the operating system you will use in the from instruction. In this example, I have chosen Ubuntu. It's important to remember that the operating systems used in containers are usually very minimal. Example, don't expect a command to be there from the start. Even commands like curl, ping, etc. may need to be installed. So that's interesting little tidbit there to know. I didn't know that. So we're learning a lot of things here so far. Building your first container. Once we have a Docker file, we can create an image using the docker build command. This command requires a few pieces of information. Number one, whether or not you want to name the image yourself, we will use the -t, then tag argument. Number two, the name that you are going to give the image. Number three, the location of the Docker file you wish to build with. I'll provide the scenario and then explain the relevant command. Let's say we want to build an image. Let's fill in the two required pieces of information listed above. Number one, we are going to name it ourselves. So we're going to use the -t argument. Number two, we want to name the image. Number three, the Docker file is located in our current working directory, which is the dot. The Docker file we are going to build is the following. So if they want to do this, once again, use from Ubuntu, and then the version work directory is going to be root, and then they're going to create that file again using run touch. The command will look like so docker build -t hello world, and then the dot. We are using the dot to tell Docker to look in our working directory. If we have filled out the command right, we see Docker starting to build the image. So docker build -t hello world and the dot, and you can see all this information as it builds out that image. Successfully tagged hello world, latest, etc. Great, looks like a success. Let's use docker image ls to now see if this image has been built. So docker image ls to list those images out. So you have hello world, Ubuntu, okay. However, whatever base operating system you list in the from instruction, the Docker file will also be downloaded. This is why we can see the two images. Number one, hello world, our image. Number two, Ubuntu, the base operating system used in our image. You will now be able to use this image in a container, refer to running your first container task to remind you how to start a container, leveling our Docker file. Okay, so I'm not sure if we're supposed to be following along with this or what. I've just been reading along with this, but I guess we can go ahead and continue here. So if you want to list it out, you can use docker image ls. Okay, let's see here, leveling up our Docker file. Let's level up our Docker file. So far, our container will create a file that's not very useful in the following Docker file. I'm going to, number one, use Ubuntu 22.04 as the base operating system for the container. Number two, install Apache 2 web server. Number three, add some networking. As this is a web server, we will need to be able to connect to the container over the network somehow. I will achieve this using the expose instruction and telling the container to expose port 80. Number four, tell the container to start the Apache 2 service at startup. Containers do not have service managers like systemd. This is by design. It is bad practice to run multiple applications in the same container. For example, this container is for Apache 2 web server and the Apache 2 web server only, okay? So this is what it looks like here. So you go ahead and just read through that yourself. For reference, the command to build this will be docker build -t web server dot, assuming the Docker file is in the same directory as where you run the command from. Once starting the container with the appropriate options, so docker run -d -name web server -p 8080 web server, we can navigate to the IP address of our local machine in the web browser. So if you were to do that, this is what it looks like here for the default page. So that you know it's working, the web server works. Currently Apache 2 is serving the default files because we have not added our own to the container. Sweet. So optimizing our Docker file. There's certainly an art to Docker, and it doesn't stop with Dockerfiles. Firstly, we need to ask ourselves why it is essential to optimize our Docker file. Bloated Docker files are hard to read and maintain, and often use a lot of unnecessary storage. For example, you can reduce the size of a Docker image and rebuild or reduce build time using a few ways. So number one, only install the essential packages. What's nice about containers is that they're practically empty from the get-go. We have the complete freedom to decide what we want. Number two, removing cached files such as apt cache or documentation installable tools. The code within a container will only be executed once on build, so we don't need to store anything for later use. Number three, using minimal base operating systems in our from instruction, even though operating systems for containers such as Ubuntu are already pretty slim. Consider using an even more stripped down version. So example would be Ubuntu :22-04-minimal, or for example using Alpine, which can be as small as 5.59 megabytes. Number four, minimizing the number of layers. I'll explain this further below. Each instruction, example from or run, etc., is run in its own layer. Layers increase build time. The objective is to have as few layers as possible. For example, try chaining commands from run together as so. So before, it would look like something like this. So they're running each individual command by itself, it looks like there, right? And they run it here with docker build-t. Okay, and then after from Ubuntu, and then you can see how they're chaining it together using these double and signs or double amperstamps, right? That you would see this as well in the terminal of like Linux if you were to do like apt get update and apt get upgrade, you know, saying like this is exactly what it would look like. So that's good to know there. Pretty straightforward. And then in the terminal, docker build-t after dot, and it goes ahead and starts running those commands there as we see. All right, so layer one from Ubuntu after, et cetera, et cetera. Okay, so we get the gist of it. You can chain those together and try to be as minimal as possible to be to optimize this as much as you can. Note here how there are now only two build steps. This will be 2 layers, making the build much quicker. This is just a tiny example of a Docker file, so the build time will not be so drastic. But in much larger Docker files, reducing the number of layers will have a fantastic performance increase during the build. So once again, we have some questions here that we need to take a look at here. Let's see, what instruction would we use to specify what base image the container should be using? Okay, then we have what instruction would we use to tell the container to run a command? What Docker command would we use to build an image using a Docker file? Let's say we want to name this image. What argument would we use? So let's go ahead and pause the video and try to answer these questions yourself. Then come back to the video and we will step through it together, and then we will proceed on. Hey everybody, this is WireDogSec. Just a quick reminder to subscribe to the channel and hit the notification bell. Once you hit the notification bell, be sure to set to all notifications so you know every time I post to the channel, upload a video, all that good stuff. Let's continue to grow our glorious community here. We are in the cyber trenches. We're not just reporting on it. Be sure to check out my channel as well. I have tons of videos that you can see here, over 300 videos ready for you to check out and learn something from. Be sure to review my posts. I'm frequently posting new things to my channel here, including jobs and everything related to that. Also, I have tons of playlists here that you can review, make it more convenient for you. Anyway, happy defending, happy hacking, enjoy the video. Let's take a look at these questions. What instruction would we use to specify what base image the container should be using? Well, that's going to be the from. What instruction would we use to tell the container to run a command? That's going to be the run. And then what Docker command would we use to build an image using a Docker file? That's going to be build. And then let's say we want to name this image file or name this image. What argument would we use? That's going to be the -t. And once again, you go back up here and reference what we just went through here. Okay, remember that's that big table up here that has the majority of what we're looking for here under the top portion here, this table instruction, description, example. So we are done with this task. Let's continue on to the next task, which is task number 5, intro to Docker Compose. Let's first understand what Docker Compose is and why it's worth understanding. So far, we've only interacted with containers individually. Docker Compose, in summary, allows multiple containers or applications to interact with each other when needed while running in isolation from one another. You may have noticed a problem with Docker so far. More often than not, applications require additional services to run, which we cannot do in a single container. For example, modern dynamic websites use services such as databases and a web server. For the sake of this task, we will consider each application as a microservice. While we can spin up multiple containers or microservices individually and connect them, doing so one by one is cumbersome and inefficient. Docker Compose allows us to create these microservices as one singular service, so that's very convenient. This illustration shows how containers are deployed together using Docker Compose versus Docker. So you have Docker by itself and then Docker Compose right there. So we can see the visible difference there in that image. Before we demonstrate Docker Compose, let's cover the fundamentals of using Docker Compose. Number one, we need Docker Compose installed. It does not come with Docker by default. Installing it is out of scope for this room as it changes depending on your operating system and other factors. You can check out the installation documentation here, or you can just use Google or a fancy AI tool out there. Two, we need a valid Docker Compose.yaml file. We will come onto this shortly. Number three, a fundamental understanding of Docker Compose to build and manage containers. I have put some of these essential Docker Compose commands in the table below. So I have command, explanation, and example up. This command will recreate / build and start the container specified in the Compose file, so docker-compose up, and I've used these in different labs and whatnot. So start, this command will start, but requires the containers already being built. The containers specified in the compose file, so docker compose start, you have down, stop, and build. So let's take a look at the other ones down. This command will stop and delete the container specified in the compose file. Stop. This command will stop, not delete the container specified in the compose file, and then build. This command will build but will not start the containers specified in the compose file. Note, these are just a few possible commands. Check out the compose documentation for all possible options. A showcase of Docker Compose. With that said, let's look into how we can use Docker Compose ourselves in this scenario. I'm going to assume the following requirements. Number one, an e-commerce website running in Apache. Two, this e-commerce website stores customer information in a MySQL database. Now, we could manually run the two containers via the following. So number one, creating the network between the two containers, Docker network, create e-commerce. Number two, running the Apache 2 web server container, Docker run -p, then 80:80, etc. Number three, running the MySQL database server, so Docker run -name database, etc. Container one, container two, so we have Apache and MySQL. An illustration shows two containers running independently of each other and is unable to communicate with another. But do we want to do this every time? Or what if we decide to scale up and get many web servers involved? Do we want to do this for every container every time? I certainly don't. Instead, we can use Docker Compose via docker-compose up to run these containers together, giving us the advantages of the following. So number one simple command to run them both. Number two, these containers are networked together, so we don't need to go about configuring the network. Number three, extremely portable. We can share our Docker Compose.yaml file with someone else, and they can get the setup working precisely the same without understanding how the containers work individually. For easy to maintain and change, we don't have to worry about specific containers using perhaps outdated images. It's very, very convenient here. I've been seeing this Docker Compose used in a lot of labs out there that helps spin up these lab environments very quickly. Okay, so here's another image of this, what they're talking about here for Docker Compose up, an illustration showing two containers deployed as a combined service. These two containers can communicate with one another. So next one is Docker Compose.yaml files 101. One file to rule them all. The formatting of a Docker Compose YAML file is different to that of a Docker file. It is important to note that YAML requires indentation. A good practice is 2 spaces, which must be consistent. First, I'll show some of the new instructions that you will need to learn to be able to write a Docker Compose.yaml file before we go into creating a Docker Compose.yaml file. So we have instruction, explanation, and example. Version. This is placed at the top of the file and is used to identify what version of Compose the Docker Compose.yaml is written for. So this example will be version 3.3 services. This instruction marks the beginning of containers being managed. And example services : name, replace value. This instruction is where you define the container and its configuration. Name needs to be replaced with the actual name of the container you want to define. Example will be web server or database. Build. This instruction defines the directory containing the Docker file for the container/servers. You will need to use this or an image. So dot/web server ports. This instruction publishes ports to the exposed ports. This depends on the image/Docker file volumes. This instruction lists the directories that should be mounted into the container from the host operating system environment. This instruction is used to pass environment variables not secure, i.e. passwords, username, time zone, configurations, image. This instruction defines what image the container should be built with. You will need to use this or build networks. This instruction defines what networks the containers will be a part of. Containers can be a part of multiple networks, i.e. web server can only contact one database, but the database can contact multiple servers. Okay. Note, these are just some of the possible instructions possible. Check out the compose file documentation for all possible instructions. Okay, that's good to know there. So it looks like we're going to take a look at an example here. With that said, let's look at our first Docker compose YAML. This Docker compose YAML file assumes the following. So number one, we'll be running one web server named web from the previously mentioned scenario. Number two, we will run database server named database from the previously mentioned scenario. Number three, the web server is going to be built using the Docker file, but we are going to use an already built image for the database server, MySQL. Number four, the containers will be networked to communicate with each other. The network is called e-commerce. Number five, our directory listing looks like the following. Number six, Docker compose YAML. Number seven, web Docker file. Here's what our Docker compose YAML file would look like. As a reminder, it is essential to pay attention to the indentation. So once again, I think they recommended 2 spaces, right? That's what they're saying earlier. And this is just showing you an example of what they have in there. And we can clearly see the indentation as they start putting this information inside of here, okay? So we got some more questions down here. Let's take a look. I want to use Docker compose to start up a series of containers. What argument allows me to do this? And that should be the up command, if I'm not mistaken. I want to use Docker compose to delete the series of containers. What argument allows me to do this? And I believe that's going to be down. What is the name of the YAML file that Docker compose uses? For this question, you will need to include the .yaml file extension in your answer. Okay. So I'll have to go back up and see which one that was. It should be this here, I believe. So we're going to copy this, plug it in. So we're done with that. Task number 6, intro to the Docker socket. This task will explain how Docker interacts between the operating system and the container. When you install Docker, there are 2 programs that get installed. Number 1, the Docker client, and then you have the Docker server. Docker works in a client-server model. Specifically, these 2 programs communicate with each other to form the Docker that we know and love. Docker achieves this communication using something called a socket. Sockets are an essential feature of the operating system that allows data to be communicated. For example, when using a chat program, there will be 2 sockets. Number 1, a socket for storing a message that you are sending. Number 2, a socket for storing a message that someone is sending you. The program will interact with these 2 sockets to store or retrieve the data within them. A socket can be either a network connection or what is represented as a file. What's important to know about sockets is that they allow for inter-process communication, or IPC. This simply means that processes on an operating system can communicate with each other. In the context of Docker, the Docker server is effectively just an API. The Docker server uses this API to listen for requests, whereas the Docker client uses the API to send requests. For example, let's take this command, docker run hello world. The Docker client will request the Docker server to run a container using the image hello world. Now, whilst this explanation is fairly basic, it is essential premise of how Docker works. Let's look at the following diagram to show the process in action. Docker client, hey, make a container with the following information: name, TryHackMe, port 80, image hello world, docker.sock. Okay, and that's going to here, and it says, okay, let's do it. What's interesting in that because of this, we can interact with the Docker server using commands like curl or an API developer tool such as Postman. Now, using this is out of scope of this room, but I'll demonstrate communication with Docker server using Postman to list all images that are stored on the program. Well, this is not working, obviously. The image isn't working. Finally, it's important to note that because of this, the host machine running Docker can be configured to process commands sent from another device. This is an extremely dangerous vulnerability if it is not correctly configured, because it means someone can remotely stop, start, and access Docker containers. Despite this, there are use cases where this feature of Docker is extremely helpful. We will cover this in further detail later in this room. Okay, I'm assuming that's going to be down here in the practical. What does the term IPC stand for? And we just saw that up here. So let's see if we can find it real quick. And there we go. Inter-process communication. So we're going to grab that and plug it in here. Next one, what technology can Docker server be equaled to? Okay, so let's go ahead. It was the API. I just now remembered. Number 7, practical. So we already have the machine booted up here. Deploy the virtual machine, start machine button, which is this here. Split screen is going to show up. If it's not there, go up here and show split view there. All right. And we have some questions here. Connect to the machine. What's the name of the container that is currently running? Okay, so we're going to clear this out. And to get running ones, I believe that was the PS. So it was Docker. And I already forgot the command. So let's see here which one it was. Syntax here. I'm not sure it was this one. Maybe in the next group. Okay, there's ls. And it should be. Let's do this. Pretty sure it's going to be that process one that we need to look at. So we already have some listed here. And maybe it was this one here that had the PS in it. Pretty sure. So let's see here. I may have just scrolled past it. There we go. There, that's what I was looking for. So it's just Docker and then PS right there. And let's go ahead and plug this in. And it says Cloud Island. It's going to be our answer there. So let's go ahead and plug that in. Next one. Use Docker to start a web server with the web server image, no quotations. You will need to run the container with port 80. After starting the container, try to connect to this here in your browser. What's the flag? Okay, so let's go ahead and try to do that real quick. I need to go check the syntax and I'll show that here on the side. All right, so this is what I have built out here. So Docker run -d-p and then port 80:80 web server. So now we see that it should be up and running now. Okay. We can see that here as we verified with the previously ran command here. And also, you can, if you don't remember out of the top of your head, you can go back and look. You can do some Googling, or you can just ask an AI tool out there. So I asked ChatGPT, I just basically copy and pasted it, gave me the information here, broke it down, what it does and everything. Okay, so now we need to go and visit this web page here and get that flag. Okay, there we go. Congrats, have a flag. And we are done with this room. Okay, so remember that the next room we're going to take a look at is going to be this container vulnerabilities room. So keep a lookout for that video coming up here. And then also I may even combine these two into one video eventually. So we're going to hit this check here and wrap up this video and close out everything that we just learned in this intro to Docker room. There was a lot of information to cover here, and hopefully y'all have stayed until the end of this video, and hopefully you have learned something. And if you want to help support the channel, be sure to like, comment, share, subscribe, and hit that notification bell so you know every time I upload to the channel. Once again, thank you all for your continued support. Be sure to note in the comment section what you mostly liked about this video. Have you done Docker before? Do you know anything about Docker? Are you new to Docker? All that good stuff. Anyway, have a nice day, and I will see you in the next one. Happy defending, happy hacking. Hey everybody, this is WireDogSec. Just a quick reminder to subscribe to the channel and hit the notification bell. Once you hit the notification bell, be sure to set to all notifications so you know every time I post to the channel, upload a video, all that good stuff. Let's continue to grow our glorious community here. We are in the cyber trenches. We're not just reporting on it. Be sure to check out my channel as well. I have tons of videos that you can see here, over 300 videos ready for you to check out and learn something from. Be sure to review my posts. I'm frequently posting new things to my channel here, including jobs and everything related to that. Also, I have tons of playlists here that you can review, make it more convenient for you. Anyway, happy defending, happy hacking, enjoy the video. Okay, so quick disclaimer here. The task 8 VM that you're supposed to be using here has some issues, at least for me. As you can see, as I was going through and trying to start up the actual container Kubernetes stuff, what have you, it did not work. It was taking a while just to get the Minikube start to run. It took about 10 minutes just to fire that off and get it running. And now when you go and check it to see if the one that you need to run this task on is running, it's stuck in this container creating. I tried resetting the review. I tried to do all kinds of things and it's just not working. So I'm letting you know ahead of time before you proceed through this video, but there is some good information in this video that can help you in learning about Kubernetes. This is the only issue that I have come across in this particular room. Hey everybody, welcome back to my channel. This is WireDogSec, back with another video for you guys. Today's video, we are in TryHackMe. This is the intro to Kubernetes room, an introduction to Kubernetes covering the basics of cluster creation and hardening. So we are learning about this container security module here. So we'll eventually have all of these completed, and then eventually I'll have them all contained in one single video as well as separate videos. But anyway, let's flip back over here and take a look at the introduction. Kubernetes. This word is very popular in the DevSecOps space. This word and the technology it represents, of course. This room is going to tell you why this is. We will take that mysterious word that everyone seems to love so much and turn it into a familiar term by walking you through Kubernetes fundamentals with a dash of secure K8s practices and sprinkle of hands-on experience to top it off, to start dispelling that mystery and save you from thinking, what the heck is K8s? Kubernetes is sometimes referred to as K8s, a numerum, anything to save time in this industry. Okay, so I guess that's how you pronounce it, K8s, whatever, K8s. We'll just say K8s. Learning prerequisites. This room will continue the DevSecOps path, so all previous SecOps modules should be completed, especially the two rooms before this one, container security module, intro to containerization, intro to Docker should be done. So check out my channel for videos related to those. And also apparently there's a learning path for this. I didn't know that until now. But anyway, learning objectives. Understand why a system like Kubernetes is needed. Understand basic Kubernetes architecture. Understand key components of the Kubernetes landscape. Understand how to traverse a Kubernetes cluster. And kubectl, understand how Kubernetes is used by DevSecOps engineers and best K8s security practices. Let's go. So we are ready to get into it. But before we do that, if you want to help support the channel, be sure to like, comment, share, subscribe, and hit that notification bell so you know every time I upload to the channel. Without further delay, let's go ahead and dive into it. Task 2, Kubernetes 101, a new dawn. To better understand Kubernetes, let us first consider the context of its emergence. In other words, why was it needed in the first place? Back in the day, it was more common for companies to have a monolithic architecture. That is, an application is built as a single unit, a single code base, and usually a single executable deployed as a single component. This worked and still works for a lot of companies. However, some companies started to switch to a microservices architecture. So instead of having one monolithic application, it would be broken down into different components. Each of these components usually having different business functions, meaning high demand business functions can be scaled without having to scale the entire application. One high-profile example of this happened in 2009, before microservices even had a name, when Netflix had issues meeting their increased demands with their monolithic architecture. So began the adoption of microservices architecture. Microservices architecture is now an increasingly popular approach, and the reason why this is so important for today's lesson is that container technologies offer the perfect host for these microservices. With microservices architecture often comprising hundreds of or even thousands of these containers, there was a need for a technology to help manage and organize them. No prizes for guessing what technology came to the rescue. Enter Kubernetes. Let's start with the big question, shall we? What is Kubernetes? In the previous rooms in this module, we discussed containers and Docker. So let's use that as our jumping off point. Imagine you have a Docker container that is running an app that can be accessed externally. Suddenly, this application starts receiving a lot of traffic, so a new container with this application needs to be spun up so the traffic can be distributed between the two. This is where Kubernetes comes in as a container orchestration system. The term orchestration conjures up images of a little orchestra, metaphor does have some traction, with the containers being like instruments and Kubernetes being the conductor and control the flow. It would just be a very strange orchestra where the conductor tells the players to leave when they're no longer needed, or the song, needed for the song, and brings new ones on when they are. Interesting there. The many benefits of Kubernetes. Now that we've established what Kubernetes is and why it's needed, let's look at how this technology can benefit the DevSecOps space. Kubernetes makes an application highly available and scalable. It does this by, for example, duplicating an application and its database component and load balancing external requests to this application to an available resource, therefore removing a single point of failure from the architecture and removing bottlenecks, which can slow down application response times. As mentioned earlier, scalability is a big concern for many companies. Kubernetes allows workflows to be scaled up or down to match demand. Kubernetes is also highly portable in that it can be run anywhere with nearly any type of infrastructure and can be used with a single or multi-cloud set, making it a very flexible tool. Another benefit of Kubernetes is its popularity. Because of this, many technologies are compatible with it and can be used to make each tool more powerful. These are just a few ways Kubernetes benefits the DevSecOps space, and it explains why that word is thrown around so much. So very good information there to learn about Kubernetes and how it became into existence. So let's check out these questions. Which benefit of Kubernetes means that it can run anywhere on any type of infrastructure? Well, that's going to be highly portable, as we saw here, right? Next one, fill in the blank. Kubernetes is a container orchestration system, as we saw earlier up here. We're just talking about that. Or container orchestration system, the term orchestration, etc., etc. So we're done with that. Task number 3, Kubernetes architecture. Cluster architecture. Okay, so we've learned about what Kubernetes is, why it's needed, and how it can benefit us in DevSecOps. Now it's time to deepen our understanding by looking under the hood and analyzing how it can be, or how it can do what it does. That's right, it's architecture time. We will go through each key component that makes up Kubernetes architecture one by one before putting it all together at the end and showing how all these components connect. Let's get into it. So we have Kubernetes pod. Pods are the smallest deployable unit of computing you can create and manage in Kubernetes. When you work in DevSecOps with Kubernetes, you'll hear a lot of this word. You can think of a pod as a group of one or more containers. These containers share storage and network resources. Because of this, containers on the same pod can communicate easily as if they were on the same machine whilst maintaining a degree of isolation. Pods are treated as a unit of replication in Kubernetes. If a workload needs to be scaled up, you will increase the number of pods running. So here's a graphic of what they're talking about here for that. All right, Kubernetes nodes. Kubernetes workloads applications are run inside containers, which are placed in a pod. These pods run on nodes. When talking about node architecture, these are two types to consider. Or there are two types to consider: the control plane, also known as master node, and worker nodes. Both of these have their own architecture / components. So let's take a look at them. Nodes can either be a virtual or a physical machine. Think of it this way: if applications run in containers which are placed in a pod, nodes contain all the services necessary to run pods. Kubernetes cluster. At the highest level, we have our Kubernetes cluster. Put simply, a cluster is just a set of nodes. The Kubernetes control plane. The control plane manages the worker nodes and pods in the cluster. It does this with the use of various components. Take a look at each of the components and what they are responsible for. Then see them all put together in a control plane architecture diagram. We have Kube API server. The API server is the front end of the control plane and is responsible for exposing the Kubernetes API. The Kube API server component is scalable, meaning multiple instances can be created, so traffic can be load balanced. Good to know there. etcd. etcd is a key value store containing cluster data, the current state of the cluster. It is highly available and consistent. If a change is made in the cluster, for example, another pod is spun up, this will reflect or will be reflected in the key value store, etcd. The other control plane components rely on etcd as an information store and query it for information such as available resources. We have Kube scheduler. The Kube scheduler component actively monitors the cluster. Its job is to catch any newly created pods that have yet to be assigned to a node and make sure it gets assigned to one. It makes this decision based on specific criteria such as the resources used by the running application or available resources on all worker nodes. And we have a kubectl manager. This component is responsible for running the controller processes. There are many different types of controller processes, but one example of a controller process is the node controller process, which is responsible for noticing when nodes go down. The controller manager would then talk to the scheduler component to schedule a new node to come up. Cloud controller manager. This component enables communication between a Kubernetes cluster and a cloud provider API. This purpose of the component is to allow the separation of components that communicate internally within the cluster and those that communicate externally by interacting with a cloud provider. This also allows cloud providers to release features at their own pace. And here's another graphic of that here. Cloud controller manager, we have etcd, scheduler, controller manager, and we have the kubectl server, API server. Kubernetes uses a hub and spoke API pattern, meaning the Kube API server is a central point of connection, the hub. Okay, good to know there. Kubernetes worker node. Worker nodes are responsible for maintaining running pods. Let's take a look at the components which are present on every worker node and what they are responsible for. So we have kubectl. Kubectl is an agent that runs on every node in the cluster and is responsible for ensuring containers are running in a pod. Kubectl is provided with pod specifications and ensures the containers detailed in this pod specification are running and healthy. It executes actions given to it by the controller manager. For example, starting the pod with a container inside. Next one is kubectl. It says is responsible for network communication within the cluster. It makes networking rules so traffic can flow and be directed to a pod from inside or outside of the cluster. Traffic won't hit a pod directly, but instead hits something called a service, which will be associated with a group of pods, and then gets directed to one of the associated pods. More on services in the next task. Container runtime. Pods have containers running inside of them. A container runtime must be installed on each node for this to happen. So far, we have covered one example of this in the module, which is probably the most popular choice, Docker. However, some alternatives can be used, such as RKT or run C. Graphic here, container runtime. So you have kubectl, kubectl, we have pods here, and it says the control plane can communicate with the node using two primary connection paths, so API server to kubectl and API server to proxy. All right. Communication between components. Okay, so we covered a lot there. Let's take a step and look at how all these individual components we've just covered work together to make up Kubernetes architecture. A Kubernetes cluster contains nodes, and Kubernetes runs a workload by placing containers into pods that run on these nodes. Take a look at the graphic below to see how all these components come together. So we can see that here. It's a pretty busy graphic here, but let's go ahead and take a look. So we have etcd, scheduler, controller manager. It could be API server. They have the cloud controller manager up here in the control plane. Here in the center, we have the other items here. Node 1 says container runtime, kubectl, kubectl, pod, and the other one seems similar as well. Node 2, then it goes from the cloud controller manager to the cloud provider API there, and this is the entire cluster from what I can gather from this. All right, so some good information there. Some questions. All right, so let's take a look here. What is the smallest deployable unit of computing that you can create using Kubernetes? Well, we know that's going to be a pod. Which control plane component is a key value store, which contains data pertaining to the clusters in its current state? And I believe that was the etcd. That's what I was looking for, etcd for that one. Okay, which worker node component is responsible for network communication within the cluster? And I believe that was the proxy, kubectl, is what we're looking for here. So we're going to plug that in, and we're going to continue on. Hey everybody, this is WireDogSec. Just a quick reminder to subscribe to the channel and hit the notification bell. Once you hit the notification bell, be sure to set to all notifications so you know every time I post to the channel, upload a video, all that good stuff. Let's continue to grow our glorious community here. We are in the cyber trenches. We're not just reporting on it. Be sure to check out my channel as well. I have tons of videos. You can see here over 300 videos ready for you to check out and learn something from. Be sure to review my posts. I'm frequently posting new things to my channel here, including jobs and everything related to that. Also, I have tons of playlists here that you can review, make it more convenient for you. Anyway, happy defending, happy hacking, enjoy the video. Task 4, Kubernetes landscape, the lay of the land. So we've just looked at Kubernetes architecture and how things work and are set up behind the scenes. Now it's time to show you the lay of the land. In other words, what as a DevSecOps engineer would you be interacting with daily? We will go through some of the most common concepts in Kubernetes and break down what they are. So we have namespaces, and Kubernetes namespaces are used to isolate groups of resources in a single cluster. For example, say you want to group resources associated with a particular component, or if you are using a cluster to host multiple tenants, to group resources by tenant, resources must be uniquely named within a namespace, but the same resource name can be used across various namespaces. A replica set, as the name suggests, a replica set in Kubernetes maintains a set of replica pods and can guarantee the availability of X number of identical pods. Identical pods are helpful when a workload needs to be distributed between multiple pods. Replica sets usually aren't defined directly, neither are pods for that matter, but are instead managed by a deployment, which brings us to our next concept. Okay, so deployments in Kubernetes are used to define a desired state. Once the desired state is defined, the deployment container or controller, one of the controller processes, changes the actual state to the desired state. The deployments provide declarative updates for pods and replica sets. In other words, as a user, you can define a deployment. Let's say, for example, test nginx deployment. In the definition, you can note that you want this deployment to have a replica set comprising 3 nginx pods. Once this deployment is defined, the replica set will create the pods in the background. Stateful sets. To understand what Kubernetes stateful sets are, you must first understand the difference between stateful and stateless apps. The stateful apps store and record user data, allowing them to return to a particular state. For example, suppose you have an open session using an email application and read 3 emails, but your session is interrupted. In that case, you can reload this application and the state will have saved, ensuring these 3 emails are still read. Stateless applications, however, have no knowledge of any previous user interactions, as it does not store user session data. For example, think of using a search engine to ask a question. If that session were to be interrupted, you would start the process again by searching the question, not relying on any previous session data. For these stateless applications, search engine example, deployments can be used to define and manage pod replicas. Because of the application's stateless nature, replicas can be created with random pod names, and when removed, a pod can be deleted at random. However, this is not the case for stateful applications, the email example, because stateful applications need to access and update the current state of the user session. Imagine this current state is being stored in a database running across 3 pods, meaning the database is replicated 3 times. Now, what happens when one of the databases is updated? This would leave 2 of the databases out of sync. This is where stateful sets come in, and is why you would use that instead of a deployment to manage stateful applications in Kubernetes. Stateful sets enable stateful applications to run on Kubernetes, but unlike pods in a deployment, they cannot be created in any order and will have a unique ID, which is persistent, meaning if a pod fails, it will be brought back up and keep this ID. So that unique ID is associated with each pod. In other words, these pods are created from the same specification but are not interchangeable. Stateful sets will have one pod that can read-write to the database, because there would be absolute carnage and all sorts of data inconsistency if the other pods could. And it says this is referred to as the master pod. The other pods, referred to as slave pods, can only read and have their own replication of the storage, which is continuously synchronized to ensure any changes made by the master node are reflected. So this is the stateful sets. We got primary over here, so it has that unique ID. There's the pod, and we have the replica, unique ID number 1 pod going here. You have the data replication going on down below here, and you have the other replica over here. All right. So this is a lot of information to wrap your heads around. Services. To best understand services in Kubernetes, it is important to understand the problem they are solving. Kubernetes pods are ephemeral, meaning they have a short lifespan and are spun up and destroyed regularly. Imagine now a connection needs to be made to these pods. This could be from within the cluster. Maybe a backend application is running in these pods and a front-end application needs to access them. Or perhaps the request is coming from a browser and these pods are running a web application. For this connection to happen, an IP address is required. If IP addresses were tied to pods, then IP addresses or these IP addresses would change frequently, causing all kinds of issues. Services are used so that a single static IP address can be associated with a pod and its replicas. In other words, a service is placed in front of these pods and exposes them, acting as an access point. Having this single access point allows for requests to be load balanced between the pod replicas. There are different types of services you can define. So we have cluster IP, we got load balancer, node port, and external name. To learn more about these types and services in general, check it out here. So I'm assuming that, yes, that goes to the documentation of Kubernetes. So check that out if you want to read more about that. And here's the graphic, what they're talking about here. So we have traffic, service, and you see it's going to these different pods down here. The source of the traffic will depend on the type of service. Ingress. So let's see what they're talking about here. In the above section of Kubernetes services, we mention an example of an application which can be made accessible by using a service to expose the pods running this application. Let's call this service A. Imagine now that this web application has a new feature. This new feature requires its own application and so has its own set of pods which are being exposed by a separate service. Let's call this service B. Now, let's say a user requests to access this new feature of the web application. There will need to be some kind of traffic routing in place to ensure this request gets directed to service B. This is where ingress comes in. Ingress acts as a single access point to the cluster. It means that all routing rules are in a single resource. And here's another graphic of what they have just explained. So if the traffic going to the ingress and it's going to either service A or service B, and that's going down to those pods there. All right. DevOps versus DevSecOps in K8s. This task has shown you some of the Kubernetes resources that work together to make a cluster. Next up, we're going to discuss how we interact with this cluster to create these components. But before we do that, this would be a good moment to discuss the division of labor in the world of K8s. It's important to understand, especially when learning for a certain career path, the difference between DevOps and DevSecOps responsibilities. At a very high level, you can think of DevOps tasks as those associated with building a cluster and DevSecOps tasks as those associated with securing a cluster. Okay, it makes sense. There will of course be some overlap depending on company architecture or corporate setup, but generally these tasks can be defined as one or the other. As this room serves as an introduction, it begins by showing you the building blocks of Kubernetes cluster and how to interact with these resources, DevOps tasks. As this knowledge is foundational, understanding these concepts will help you in the later task when we discuss securing the cluster, DevSecOps task. That being said, as mentioned, the distinction is important, especially for those pursuing a specific career path, so keep this in mind going forward. So let's get to know there. All right, so let's take a look at these questions here. Which Kubernetes component exposes pods and serves as an access point? Well, that's going to be the service, as we read above. Which Kubernetes component can guarantee the availability of X number of pods? That's going to be the replica set. And what Kubernetes component is used to define a desired state? That's going to be deployments. Task number 5 here, Kubernetes configuration. Time to configure. Now that we've covered some of the key components used in Kubernetes, let's combine some of them and walk you through how this would be configured. The example we will use is a deployment which controls a replica set which manages pod exposed by a service here. Okay. To configure the setup, we would require 2 configuration files, one for the deployment and one for the service. Before giving you an example of how each of these files work, let's go over some of the basics of configuration in Kubernetes that will be consistent across these two files and all configuration files for that matter. First, let's discuss the file format. Kubernetes config files are typically written in YAML. They can also be made interchangeably using the JSON format, but as per Kubernetes documentation, it is generally considered best practice to use YAML given its easy, human-readable nature. Just got to keep an eye on that indentation. Okay, so we have required fields. Next, let's discuss the 4 fields which must be present in each of the YAML files, breaking down what will need to be included in each one. So the first one is going to be the API version, the version of the Kubernetes API you're going to use to create this project or object. The API version you use will depend on the object being defined. A cheat sheet for what API version to use for which object can be found here, so feel free to check that out. Kind, what kind of object you are going to create. Examples would be deployment, service, or stateful set. Metadata, this will contain data that can be used to uniquely identify the object, including name and an optional namespace. Spec, the desired state of the object. For deployment, this might be 3 Nginx pods. We have configuration resources as the last one here. So those are the very basics of Kubernetes YAML configuration files. Okay, yeah, so the last one was spec. Now we're going to talk about configuration resources. Okay, so let's consider those and look now at the 2 files mentioned above. We're going to take a look at the service config file first, as when defining a deployment and service, it is generally best practice to first define the service before the back-end deployment / replica set that it points to. This is because when Kubernetes starts a container, it creates an environmental variable for each service that was running when a container started. Here is what our example service.yaml file looks like here. So we have the API version, version 1, kind, service, metadata, the name, example Nginx service, spec, selector, app Nginx, ports, you have protocol TCP, you have the port, which is 8080, target port is going to be 80, and type cluster IP. Let's break down each component here. So API version is set to version 1, the version of the Kubernetes API best used for this simple service example, and kind is set to service for the metadata. We just called this service example Nginx service. The spec is where it gets more interesting. Under selector, we have the app Nginx, which it says this is going to be important going forward when we define our deployment configuration, as is the ports information, as we are essentially saying here. This service will look for apps with Nginx label and will target port 80. An important distinction to make here is between the port and target port fields. The target port is the port to which the service will send requests. Example, the port the pods will be listening on. The port is the port the service is exposed on. Finally, the type is defined as cluster IP. Earlier, we discussed that there were multiple types of services, and this is one of them. It says which is the default service type. Now let's take a look at the deployment YAML and define the back end which the service will point to. Once again, we have similar items here: apps v1, deployment, metadata, example Nginx deployment, replicas 3, selector, etc., etc. So we're going to talk about it here, I'm assuming. Let's see here. The first thing you might notice is that inside the spec field, there's a nested field called template, which itself contains a metadata and spec field. To understand this, remember the image at the start of this task. We are defining a deployment which controls a replica set. Here is the outer spec field. We tell Kubernetes we want 3 replicas, identical pods. In this replica set, this template field is the template that Kubernetes will use to create those pods, and so requires its own metadata field so the pod can be identified, and spec fields so Kubernetes knows what image to run and which port to listen on. Note that the port defined here is the same as the one in the service YAML. This is because the service's target port is 80 and needs to match, as well as this. In the outer spec field, you can see we have also set the selector field to have a match labels, which matches what we define in the selector field for the service YAML. This is so the service is mapped to the correct pods, with these two config YAML files, we have defined a deployment that controls a replica set that manages 3 pods, all of which are exposed to a service. It's all coming together. These config files are used to define the desired state of Kubernetes components. Kubernetes will constantly be checking this desired state against the current state of the cluster. Using the etcd, one of the control plane processes mentioned in an earlier task, Kubernetes populates these configuration files with the current state and does this comparison. For example, if we told Kubernetes we want 3 Nginx pods running and it detects in this status that there are only 2 running pods, it will begin the actions to correct this. Interesting. So let's check out these questions. In a config file, you have just declared that you want 4 Nginx pods, and which of the required fields has this been declared? So 4 Nginx pods, and I would say that needs to go into the spec field for that one. The configuration file is for a deployment, and which of the required fields is this declared? And this one's going to be kind, so see kind deployment, and then the last one's going to be 80, right? It says the pods in this deployment will be exposed by a service. In the service configuration file, the target port was set to 80. What should you put as the container port? So I believe it said that it needs to match, right? So it's going to be 80 for that one. Task number 6, kubectl. kubectl to the rescue. We've just covered how to define the desired state of your cluster using YAML config files, but currently those exist only as files. To take these from configurations to running processes, we need to interact with the cluster. We can do this by interacting with the API server component of the control plane using different methods. So we have the user interface, if using the Kubernetes dashboard, the API, if using some sort of script or command line using a tool called kubectl. This task focuses on the last of these. Simply put, kubectl is a command line tool provided by Kubernetes that allows us to communicate with a Kubernetes cluster's control plane and is a great addition to our DevSecOps arsenal. This task will show you how to take the config files outlined in the previous task and apply them, as well as give you some bootcamp training for this tool, teaching you some of the basic commands so you can navigate a Kubernetes cluster like it's your own back garden. kubectl apply. Once you have defined your deployment and service configurations in the YAML file, the next step would be to apply them so Kubernetes can take the desired configuration and turn it into a running process. This is done using the aptly named apply command. For example, if applying the service YAML mentioned in the previous task, that would look like this. So we have kubectl, you have apply -f, example deployment.yaml. kubectl get. Once both configurations have been applied, you'll want to check the status of both to ensure things are running as expected. This will be done using kubectl get command. This is a very versatile command, and you will be using it a lot in your time with Kubernetes. The get command can be used to check the state of resources. The resource type will follow get, then -n or -- namespace, followed by the namespace, unless you are checking a clustered level resource like a node. For example, to check the state of a deployment, you would use kubectl get pods -n and then example -namespace. The output for this command will look something like this. So we have the same thing here, kubectl get pods -n example namespace, and it gives you that output or the results back for that. As mentioned, this command can be used to check on a variety of resources such as deployments, services, pods, and replica sets. kubectl describe. This command can be used to show the details of a resource or group of resources. These details can help in troubleshooting or analysis situations. For example, say one of the pods in your cluster has started erroring out, and you want to get more information about the pod to try to determine why it has crashed. You would run the following command. So we have kubectl describe pod example -pod -n example -namespace. This would give you back some details about the erroring pod, for example. Do you run all that there? It gets you back to name, namespace, the priority, service account, node information, the start time, labels, annotations, status, and IP address, and then probably some more stuff there. You can see here that the describe command details contain some events. These events can help shine a light on what the issue is. For more details surrounding this event, Kubernetes captures the logs from each container in a running pod. These logs can be viewed using our next command, which is going to be kubectl logs. Say you want to view the application logs of the erroring pods. Maybe you want to view the logs surrounding the event error. For this, we would use kubectl logs command. Here is an example how that would be used. So we have kubectl logs, example dash pod dash end, example dash namespace. These logs can provide valuable insight, not just for troubleshooting, but for security analysis as well. Good to note there. kubectl exec. Now let's say the log information was helpful, but there are still some unanswered questions, and you want to dig deeper to access the container shell. The kubectl exec command will allow you to get inside a container and do this. If a pod has more than one container, you can specify a container using the -c or -- container flag. The command for this is the -it flag. Runs the command in interactive mode. Everything after the -- will be run inside the container. Okay, and here's an example for that. So we have kubectl exec -it. Example pod -n, example namespace --sh. From here, you can run any command you want from within the container itself. Maybe you want to snoop around for security analysis or run a command to test connectivity from the container. All right, so we're going to talk about this last one here. kubectl port to forward. Another handy command is kube port to forward. This command allows you to create a secure tunnel between your local machine and a running pod in your cluster. An example of when this might be useful is when testing an application. Let's imagine we have an Nginx web application running across 3 pods, which are exposed by a web application service. If you remember, a service makes a pod externally accessible. We take the port that is used to expose these pods and map it to one of our local ports. For example, matching the target port, the port the service is exposed on, which in our configuration example was 8080 to local port 8090, would make this web application accessible on our local machine at HTTP localhost port 8090. The resources specified are resource type / resource name. This would be done by using kubectl port to forward command with the following syntax. So we have kubectl port to forward service example service 8090 8080. There are, of course, plenty more kubectl commands that can be used to navigate and interact with Kubernetes cluster, but the ones covered give you a solid foundation, and you can perform some day-to-day DevSecOps tasks using only these. You will get a chance to demo these commands in this room's practical exercise in task 8. Now complete these questions. What command would follow kubectl if you wanted to do the following here? Okay. Let's see if we can answer these real quick. So troubleshoot a pod by gathering some details about it, and that should be in the I believe the scribe for this one, right? So let's go ahead and plug that one in. Access the container shell, and that was the exec to do that, because you have to use that. You can use that -it command to interact with it, right? Check the status of running pods. Okay, and that's going to be I believe that's going to be logs, but actually let's see here. Okay, that's going to be get, because it displays the status there. So get's going to be that one. So we'll plug that in as our answer. And last one, turn a defined configuration YAML file into a running process. Okay, and that one I believe is going to be apply. So we're going to get that one in here. And we're going to talk about task number 7 here, Kubernetes and DevSecOps. So let's see what they're talking about here. First, let me scroll down a little bit here. So it's going to be, looks like quite a bit of reading as well. Okay, so let's see here. Okay, by now you're getting pretty familiar with Kubernetes. It's becoming less of an acquaintance and more of a friend. You've learned the ins and outs of the tool and will soon get a chance to have a hands-on demo of it. But before any of that, let's look at exactly how you would use this tool as a DevSecOps engineer. After all, that's very likely why you're here. Okay. Kubernetes and security. Before we dive into what a DevSecOps engineer would be responsible for in a Kubernetes cluster, let's consider Kubernetes from a security perspective to give some context. Kubernetes is, relatively speaking, new on the block. That is to say, it is an emerging technology. It's emerging but very popular, with many companies adopting Kubernetes, especially young tech and startup companies. Introducing any tool into a system is considered an increased security risk, as a new tool means a new potential way into that system. These risks are amplified when dealing with a tool like Kubernetes, where you have a network of pods that can communicate with each other. The default setting allows any pod to communicate with another. This implies all kinds of security considerations. As a DevSecOps engineer, it is your responsibility to ensure these channels are secure. Kubernetes hardening. Container hardening is one way in which DevSecOps engineers can secure these channels. We will dive into that later in this module with the container hardening room. It is the process of using container scanning tools to detect CVEs present in a cluster and remediate them to ensure minimal security breach risk. Kubernetes hardening is precisely that, ensuring these channels are secure by fortifying your cluster, following best container security practices that you would perform as a DevSecOps engineer. Various companies and government agencies have defined these best practices. Let's go over each area in which we can strengthen our container security and how this can be done. So we have secure pods. Let's begin with a few ways to secure pods themselves. Some best practices for pod security include the following. But containers that run applications should not have root privileges. Containers should have an immutable file system, meaning they cannot be altered or added to depending on the purpose of the container. This may not be possible. Container images should be frequently scanned for vulnerabilities and misconfigurations. Privileged containers should be prevented. Pods security standards and pod security admission. So be sure to check those two out. Hardening separation of your network. In the introduction to this task, one thing especially was flagged as a big security risk: communication. That communication happens over a network, and it's your job as a DevSecOps engineer to ensure this communication is secure. This can be done using the following best practices. So we have access to the control plane. Nodes should be restricted using a firewall and role-based access control in an isolated network. Control plane components should communicate using transport layer security, or TLS for short. So you're going to be using TLS certificates. An explicit deny policy should be created. Credentials and sensitive information should not be stored as plain text in configuration files. Instead, they should be encrypted in Kubernetes secrets. Using authentication and authorization optimally. It wouldn't be a security lesson if we didn't talk about authentication and authorization. Of course, Kubernetes is no different. Here are some of the best practices which can help make sure you are making efficient use of Kubernetes authentication and authorization features. Anonymous access should be disabled. Strong user authentication should be used. RBAC policies should be created for the various teams using the cluster and the service accounts utilized. Keeping an eye out. You can't rest easy knowing your Kubernetes cluster is secure if you don't know what's going on in your Kubernetes cluster. Here are some logging best practices to ensure you know exactly what is going on in your cluster and can detect threats when they appear. So you have audit logging should be enabled. A log monitoring and alerting system should be implemented, right? A SIM tool. So you're going to be sending these logs back to your SIM tool, that centralized location, right, to collect those logs. Security never sleeps. This is no way an endorsement of sleepless life cycle. DevSecOps engineers do in fact need to sleep. Being secure is one thing, staying secure is another. Here are some best practices to ensure your cluster stays a safe haven. Security patches and updates should be applied quickly. Vulnerability scans and penetration tests should be done semi-regularly. Any obsolete components in the cluster should be removed. All right, so we have Kubernetes security best practices in action. The above information tells us there are a lot of ways to harden a Kubernetes infrastructure. There are so many, in fact, that breaking down each practice would turn this room into a self-published ebook. With the opportunity to get your hands on Kubernetes just a task away, let's finish this one by breaking down just 3 of them. First one up is going to be RBAC, which is the role-based access control. And Kubernetes regulates access to a Kubernetes cluster and its resource based on defined roles and permissions. These permission to create /delete X source, etc. It says are assigned to users, groups, or service counts. RBAC is a good way to ensure the resources in your cluster can only be accessed by those who need to access it. RBAC can be configured using a YAML file, same as defining a resource, where specific rules can be applied by declaring the resource type and verbs. Verbs are the actions being restricted, such as create and get. Okay, so that goes back to the, the principle of least privilege and whatnot. See how that applies here in various different areas and technologies in cybersecurity. Secrets management. A Kubernetes secret is an object used to store sensitive information like credentials, OAuth tokens, or SSH keys. Secrets are a good way to ensure that sensitive data isn't leaked and allow for more control over how this information is used. Secrets are stored as a base 64 encoded string, unencrypted by default. For security, it is best to configure encryption at rest. Another way to promote secure secrets management in your Kubernetes cluster is to configure the least privilege access to secrets using RBAC, right? As I just mentioned that earlier, least privilege. PSA, which is Pod Security Admission, and PSS, which is Pod Security Standards. Pod Security Standards are used to define security policies at 3 levels. You have privileged, baseline, and restricted. At namespace or cluster-wide level, what these levels mean. Privilege, since this is a near unrestricted policy, allows for known privilege escalations. Baseline, this is a minimally restricted policy and it will prevent known privilege escalations. Allows deployment of pods with default configuration. We have restricted. This heavily restricted policy follows the current pod hardening best practices. Pod security admission, using a pod security admission controller, enforces these pod security standards by intercepting API server requests and applying these policies. Note, previously, the roles of PSA and PSS were fulfilled using PSPs, which is pod security policies. However, as of Kubernetes version 1.25, these have been removed. Just to save any confusion, if you stumble across PSPs doing some extracurricular Kubernetes security study. As you can see, a lot goes into fortifying Kubernetes cluster and planning to keep a DevSecOps engineer busy. These are some of the best practices involved in Kubernetes hardening. DevSecOps engineers, while following these practices and utilizing techniques such as automated security checks, can ensure the Kubernetes environment is safeguarded against cyber threats. So that's a lot to take in there to harden these and secure these environments here. All right, so the questions here, let's take a look here. Which best container security practice is used to regulate access to a Kubernetes cluster and its resources? That's going to be RBAC, or role-based access control. What is used to define security policies at 3 levels? That's going to be pod security standards. What enforces these policies? That's going to be pod security admission. And what Kubernetes object can be used to store sensitive information and should therefore be managed securely? That's going to be secret. All right, now we're going to get to task number 8, hands-on with Kubernetes. I've already started the machine here, so just click that start machine button. It'll fire up in split view. All right, phase 1, explore. Okay, let's get going, shall we? The first thing we want to do is start our Minikube cluster. You can do this by running the following command in the terminal. The cluster will take a couple minutes to start up, so I'm just going to copy and paste this over like so. Okay. That's Minikube start. And it says, once the cluster has started up, you're ready to go. This guided walkthrough will take you through this cluster, reinforcing knowledge taught in the room. That being said, you have a Kubernetes cluster at your disposal, so feel free to explore the cluster and experiment with the different commands you've learned so far. So very important there. Let's see what's running already, shall we? We can do this using the following command, which is -A for all namespaces. So we're going to use kubectl get pods -A. So after running this, you should see a few pods running. These are the default pods present when you first start a Kubernetes cluster. You may recognize some of these names as they represent some of the control plane and worker node processes. Exciting stuff. But how about we make it more exciting by adding a deployment and service into the mix? On the VM, you will be able to find some config YAML files located in desktop configuration. Okay. Looks like it's still firing up here. But anyway, so inside of there, it says cat file name. Let's break down what we see in each of these files. All right, so as soon as this finishes running, but let's see if we can just open up a new tab here and just if we could take a peek at it. So we're going to cd into the directory here, which is in desktop, and then it's going to be into that configuration folder there. Okay, so there we go. We have a couple in here, nginx deployment.yaml and nginx servers.yaml. So if we want to take a look at one of these here, the deployment, there we go. Okay, and then there's also that other one in there. So clear the screen here, and we're going to do the same thing. And it was the service, right? So that's the other one. Take a quick peek at there. So let's see if this is finished. And it's still going, I guess. Okay, so nginx deployment.yaml. This is a relatively simple deployment. We can see the desired state has been defined as a single replica pod, inside of which will be a container running an nginx image. From the other lines, we can see, or we can determine that this pod will be used to run some kind of web app, right? All right, so if we want to take a look at that again real quick inside of here. So deployment, nginx deployment, replicas 1, app nginx, right? Nginx, web app volume, HTML, web app config. Next one is going to be the nginx servers.yaml. This again is a straightforward nginx node port service being defined here. So let's bring that one back up again. All right. The eagle-eyed among you may have noticed that the selector app field matches the app label defined in the deployment, as well as the target port matching the container port outlined in the deployment. This service exposes the web application running in the pod, which the deployment controls. To apply the configuration outlined in these YAML files, we use the kubectl apply command. Remember to apply the service first, or service file first, like so. All right, so let's see if this is done yet. All right, I guess it might still be going. Let me wait a few minutes. I'll come back and then see if we can start doing this here. All right, it finally finished after about 10 minutes or so. So let's go ahead and continue on here. I know they wanted us to try this out at the beginning of this task, so we're going to plug this in here. See what that looks like here. All right, so we have some things running there. And now we're going to get to the apply stuff here. So we're going to apply that service first, and then the other one after that. Okay. Oh, that's right. I need to. Let's just go to the. I'm just going to open up a new tab here, and just make this a little bit bigger. All right. So let's see. We need to cd into desktop, and then cd into configuration. Right, and then there's our files there. So we're going to paste this in. There we go. And now the other one here. Okay, so now we should be good. It says verify the replica pod is running by using the following command, not providing any namespace flag. We'll get all the pods in the default namespace, which is where our pod should be. So we're going to run this again. Right, so I'm just going to just up arrow. Okay, so it looks like we are good to go here from what I could tell here, nginx, right? So let's go ahead and continue on. Says you should now see a pod with nginx deployment in its name. Our deployment has been started. Phase 2, interact. Okay, now we have a web application running in a pod, which is being exposed by a service. If you recall the nginx service YAML, the service connects to a web application using the target port 80. The port where the container is exposed. However, the service's port itself is set to 8080. We want to access the service. We will do this by using the kubectl port forward command, which allows us to forward a port on our local host to the Kubernetes service port 8080. Here's the full command. Okay, so we have a kubectl, port forward service and Nginx, and they have service port 8090 to 8080. So let's go ahead and paste that in there. It's not running. Okay, so I guess we have to give it a few minutes to fire up completely. All right. Well, I wish it would mention that in this task that it takes a while for this to fire up or something. Yeah. So let's give it a few more minutes and see if this actually starts running. It still says container creating. Okay. Unfortunately, this is not working. As you can see, it still says container creating, and I've waited at least 30 minutes, and I am not about to wait any longer. So we're just going to read through this, and I just went ahead and looked at a write-up to get the answers. Okay, so anyway, so let's go ahead and just follow along here. All right, so once this is up and running, you should be able to use the port forward command here and then navigate to it via the Firefox web browser. All right, via this URL. Hopefully this worked out for y'all. Obviously it did not work out for me. So this looks like a simple login terminal, but it needs credentials. Why don't you see if there's any in the Kubernetes secret on the cluster that can help us log into the terminal. Open another terminal window, go to the previous window, continue to port forward and follow or run the following command to see if there are any secrets in the default namespace. Okay, I guess we can go ahead and try that, but I doubt it's going to work. But let's see here. All right, so let's just paste that in there. Right, so right, as I was saying, there it is, terminal creds. Sounds like we are onto a winner. Using the kubectl describe command, we can get more details on the secret to see what it is being stored there. So if this was working for you, you can just run this here, kubectl describe secret terminal creds. In the description, we will see that two pieces of data are being stored, a username and a password. While Kubernetes secrets are stored in plain text and are not encrypted by default, they are base64 encoded. So we pipe this command and base64 decode the output to get it into plain text to access this data. We can use the following command. So if you wanted to decode that, you can use this here in the terminal for the username, then again for the password. All right. Use these credentials to access the login terminal. That's a bingo. We're in. And you have retrieved the flag. Bonus task. For those curious enough, you can use an alternative method to get this flag. It will require some Kubernetes investigation on your part, but the first breadcrumb lies in the nginx deployment.yaml file. Okay. If this was working for you, go ahead and try that yourself. Phase 3, secure. It's great that we could access the terminal using the credentials stored in the Kubernetes secret, but as a DevSecOps engineer, this is where our alarm bells should be going off. Time for us to get to work with some Kubernetes secret management. With these credentials being sensitive information, we want to restrict access to the Kubernetes secret they are stored in. We can do this by running the RBAC, which is the role-based access control. We're going to configure the RBAC to fix that issue. First things first, let's decide who it is we want to be able to access the secret. Your DevSecOps manager has suggested that you restrict access to a service account, which is essentially an identity a pod can assume to interact with the Kubernetes API/cluster. By doing so, we can maybe even set it up so that in the future, our daily terminal tasks can be run by an application in a pod. Let's use the kubectl create service count, can be abbreviated to SA command to make two service counts. The terminal user for non-admin terminal activities should not have access to the secret, and the terminal admin for admin terminal activities should have access to the secret. Run these two commands to make those service counts. So if you were to do that, you can do it this way here. Kubectl create SA terminal user and then do it again for the terminal admin. With those service counts created, it is time to restrict access to the terminal creds secret so that only the terminal admin service count can access it. We're going to do this by defining and applying two configurations. First of all, a role YAML that defines the role and what it can do, get the terminal cred secret, then a role binding YAML that binds the role we have defined to the terminal admin service count. Navigate to the following directory and cat the two YAMLs to examine how these are defined. Okay, so I guess we can follow along here and see how far we can get on this. All right, so let's go ahead and cd into that area here. Okay, so there we go. Here you can see we define a role named secret admin. In the role section, we define what it is the role can do. We can define the resources, secrets, what verbs are being restricted. We are restricting the get verb, but you could restrict others. Finally, the name of our secret, terminal creds. Okay, so I'm assuming we need to just cat these. So let's cat this first one here. There we go. This one's for the terminal admin, right? And then the other one should be for the non-admin account. So let's go ahead and just cat that one as well. Let's see here. There we go. Okay, so yeah, secret admin, terminal creds. Okay, so we're going to talk about this one. Looks like role binding.yaml. In this YAML, we bind the terminal admin service account in the subject section with the secret role admin role defined above in the role ref section. Now let's apply these configurations the same way we apply the deployment and service using the kubectl apply. So if we were to do that, kubectl apply -f role.yaml, and then what you do it again with role -binding.yaml. You have now configured RBAC for this Kubernetes secret. The only thing left is to test whether our RBAC is working. We can do this using the kubectl auth command, which tells us if a service account has sufficient permission to perform a specific action. Let us first verify that the regular terminal user service account cannot access the secret. So if we were to do this, you can do it like this. Kubectl auth can I get secret terminal creds -- as system, and then service account default terminal user. So they're going to test it out as it stated earlier with that just non-admin account, see if it is going to have access or not. It looks like we expected. This no response confirms that the service account can no longer access the terminal cred secret. Now finally, let's verify that our terminal admin service account can access it. So you're going to do the same thing, except you're going to switch it with the terminal admin. With this yes output, you have confirmed RBAC is in place and fulfilled your duty as a DevSecOps engineer, fortifying the cluster and taking a good first step into hardening this cluster. Hope you've enjoyed taking a little tour around the Kubernetes cluster and getting to know the basics. Till next time. All right, anyway, so if you were to get this, hopefully it worked for y'all, right? You should be able to get the flag, and then this other one too that says what API version is used for role binding. All right. We can actually see this one here in the cat role.yaml. So we can go ahead and just grab that, and we can see it in the other one as well. So both of these appear to have that in there. So we're at least able to get one of these without looking it up. But anyway, I'm going to check it one last time and see if it actually came up. No. Okay, anyway, so we are going to close this video out, and I'm going to try to put this issue at the beginning of this video so that people will be aware before going through this room entirely. But hopefully you'll have gained some knowledge about Kubernetes, how it came about, how it works, the different features of it, how to identify some possible security related issues, how to fix those issues, all that good stuff. And if you enjoyed the video, enjoyed the content, and you want to help support the channel, be sure to like, comment, share, subscribe, and hit that notification bell so you know every time I post or upload to the channel. Thank you. Have a nice day. I will see you later. Happy hacking and happy defending. Hey everybody, this is WireDogSec. Just a quick reminder to subscribe to the channel and hit the notification bell. Once you hit the notification bell, be sure to set to all notifications so you know every time I post to the channel, upload a video, all that good stuff. Let's continue to grow our glorious community here. We are in the cyber trenches. We're not just reporting on it. Be sure to check out my channel as well. I have tons of videos that you can see here, over 300 videos ready for you to check out and learn something from. Be sure to review my posts. I'm frequently posting new things to my channel here, including jobs and everything related to that. Also, I have tons of playlists here that you can review, make it more convenient for you. Anyway, happy defending, happy hacking, enjoy the video. Hey everybody, welcome back to my channel. This is WireDogSec, back with another video for you guys. Today's video, we are in TryHackMe. This is Container Vulnerabilities room. Learn how some of the common vulnerabilities found within Docker containers can be exploited. So let's take a look at this room and see what they are cooking with. Task 1, Introduction. This room will demonstrate some of the common vulnerabilities found in Docker containers and how an attacker can abuse these to escape. Learning objectives. In this room, you will learn the following: some of the vulnerabilities that can exist in a Docker container, what you as an attacker can gain from exploiting these vulnerabilities, why these vulnerabilities exist, i.e. misconfiguration, how to search for vulnerabilities within a Docker container. Prerequisites. Before proceeding, it is strongly recommended that you complete the Intro to Docker room and are comfortable with the Linux CLI, or check out my channel for videos related to both of those. Important context. The room focuses on exploiting the Docker daemon itself, which often relies on having elevated permissions within the container. In other words, this room assumes that you have already managed to become root in the container. Deploy the vulnerable machine for this room. We already done that, so start machine button up here at the top, and this is the information to access it, so we'll hop on this in a minute. It says use credentials below via the TryHackMe attack box, or by connecting your machine to TryHackMe network, so using the VPN. And it says complete me to progress with this room. So I'm going to go ahead and start up the attack box, get that ready to go. And also, before we proceed, if you want to help support the channel, be sure to like, comment, share, subscribe, and hit that notification bell so you know every time I upload to the channel. Without further delay, let's go ahead and dive into it. Task 2, Container Vulnerabilities 101. Before we begin, it's important to recap some of the things learned in the Intro to Containerization room. First, let's recall that containers are isolated and have minimal environments. The picture below depicts the environment of a container, a diagram demonstrating 3 containers on a single computer. So you have container 1, 2, and 3, application environment, okay, for each of these, and they have the Docker image, then the computer operating system, the host, and the physical computer. Some important things to note are, just because you have access, example would be a foothold, to a container, it does not mean you have access to the host operating system and associated files or other containers. Due to the minimal nature of containers, example, they only have the tools specified by the developer. You are unlikely to find fundamental tools such as netcat, wget, or even bash. This makes interacting within a container quite difficult for an attacker. What sort of vulnerabilities can we expect to find in Docker containers? While Docker containers are designed to isolate applications from one another, they can still be vulnerable. For example, hard-coded passwords for an application can still be present. If an attacker is able to gain access through a vulnerable web application, for example, they will be able to find these credentials. You can see an example of a web application containing hard-coded credentials to a database server in the code snippet below. So if we look at this example here, database hostname, okay, localhost, database name, sales, database user, production, database password, strong password 321 exclamation point, and there we go. This, of course, isn't the only vulnerability that can be exploited in containers. The other potential attack vectors have been listed in the table below. So let's take a look at this table. You have vulnerability and description. Misconfigured containers. Misconfigured containers will have privileges that are not necessary for the operation of the container. For example, a container running in privileged mode will have access to the host operating system, removing the layers of isolation. Next one, vulnerable images. There have been numerous incidents of popular Docker images being backdoored to perform malicious actions such as crypto mining. Network connectivity. A container that is not correctly networked can be exposed to the internet. For example, a database container for a web application should only be accessible to the web application container, not the internet. Additionally, containers can serve to become a method of lateral movement. Once an attacker has access to a container, they may be able to interact with other containers on the host that are not exposed to the network. This is just a brief summary of some of the types of vulnerabilities that can exist within a container. The task in this room will delve into these further. Click to proceed to the next task. So let's go ahead and do that. And task number 3, we're going to talk about vulnerability 1, privileged containers, capabilities. Understanding capabilities. At its fundamental, Linux capabilities are root permissions given to processes or executables within the Linux kernel. These privileges allow the granular assignment of privileges rather than just assigning them all. These capabilities determine what permissions a Docker container has to the operating system. Docker containers can run in 2 modes. You have user, normal mode, and you have privilege mode. In the diagram below, we can see the two different modes in action and the level of access each mode has to the host. So let's look at this diagram. A diagram demonstrating the difference of container mode privileges. Container 1, normal mode, application 1, environment, Docker engine. Container 2, normal mode, application 2, environment, Docker engine. Container 3, privilege mode, application 3, environment. And this goes to the computer operating system, which is the host. All right. Note how containers 1 and 2 are running in user/normal mode, whereas container 3 is running in privilege mode. Containers and user mode interact with the operating system through the Docker engine. Privileged containers, however, do not do this. Instead, they bypass the Docker engine and directly communicate with the operating system. What does this mean for us? Well, if a container is running within privileged access to the operating system, we can effectively execute commands as root on the host. We can use a utility such as capsh, which comes with the libcap2-bin package to list the capabilities of our container, or the capabilities our container has. So capsh and then --print will do that. Capabilities are used in Linux to assign specific permissions to a process. Listing the capabilities of the container is a good way to determine the syscalls that can be made and potential mechanisms for exploitation. Some capabilities of interest have been provided in the terminal snippet below. So let's see here. Listing capabilities of privileged Docker container, capsh --print, and then it lists out everything here: chown, sysmodule, chroot, sysadmin, sit gid, sit uid. In the example exploit below, we are going to use the mount syscall as allowed by the container's capabilities to mount the host control groups in the container. The code snippet below is based upon, but a modified version of proof of concept created by TrilBits, which details the inner workings of this exploit well. So let's see here. Oh, okay, you can't make it bigger. But let's see here. It's going to explain it down here, I guess, but we can see a little snippet up here what they're doing. Explaining the vulnerability, we need to create a group to use the Linux kernel to write and execute our exploit. The kernel uses C groups to manage processes on the operating system. Since we can manage C groups as root on the host, we'll mount this to temp C group on the container, which they're doing up here. Number 2, for our exploit to execute, we'll need to tell the kernel to run our code by adding 1 to temp C group X notify on release. We're telling the kernel to execute something once the C group finishes, okay? Number 3 here, we find out where the container's files are stored on the host and store it as a variable. Number 4 here, we then echo the location of the container's files into our exploit, and then ultimately to the release agent, which is what will be executed by the C group once it's released. Number 5 here, let's turn our exploit into a shell on the host. Number 6 here, execute a command to echo the host flag into a file named flag.txt in the container once exploit is executed. Number 7, the chmod up here, make our exploit executable. Number 8 here says we can create a process and store that into temp cgroup xgroup.procs. When the process is released, the contents will be executed. Nice. Okay, so support the exploit in the task on the target machine. What is the value of the flag that has now been added to the container there? Okay, so let's just look at this hint real quick and see what it says. Remember, it says remember where, all right, that was weird. Remember where the payload for the exploit is being stored in the, it looks like, root directory. Okay, so go ahead and pause the video and try to do this yourself, and then we'll come back and step through it together. Okay, we're just about ready to rock and roll. All right, so to connect to this container, make sure to use SSH. So you can SSH into it, root at whatever IP address you got, and then use those credentials. Now, we're going to use this here to see what we have. So this is listing out everything as explained in this here, listing capabilities of privileged Docker container. Okay, so now we're going to go through these steps here to get that flag. So I'm going to copy and paste everything here to make it easier to do. And let's go ahead and clear the screen out here. Okay, so I guess we are done, and now we just got to get the flag, and they said it's going to be in root. So let's see where we are right now. So we can use just pwd. Oh, okay. Well, ls, nothing in here. Let's go back one, ls, and there's the flag. So we're just going to go ahead and cat that bad boy. Got it. Good to go there. And let's plug that in and continue on here to task number 4. Vulnerability 2, escaping via exposed Docker daemon. Unix Sockets 101. One size fits all. When mentioning sockets, you would likely think of sockets in networking. Well, the concept here is almost the same. Sockets are used to move data between two places. Unix sockets use the file system to transfer data rather than networking interfaces. This is known as inter-process communication, IPC, and is essential in operating systems because being able to send data between processes is extremely important. Unix sockets are substantially quicker at transferring data than TCP/IP packets. This is why database technologies such as Redis boast such outstanding performance. Unix sockets also use file system permissions. This is important to remember for the next heading. How does Docker use sockets? When interacting with the Docker engine, running commands such as docker run, this will be done using a socket. Usually this is done using a Unix socket unless you execute the commands to a remote Docker host. Recall that Unix sockets use file system permissions. This is why you must be able or be a member of the Docker group or root to run Docker commands, as you will need permissions to access the socket owned by the Docker. Okay, so you can do this via here, verifying that our user is part of the Docker group, just using groups here, right, to list that out. So I'm going to be lazy and just copy and paste this. So let's go ahead and clear all this stuff out. So we don't need it anymore. There we go. So like I said, you could be a member of the Docker or just root. So we're obviously root. Finding the Docker socket in a container. Remember, containers interact with the host operating system using the Docker engine and therefore have access to Docker socket. This socket named docker.sock will be mounted in the container. The location of this varies by the operating system the container is running. So you want to find it. However, in this example, the container runs Ubuntu 18.04, meaning the docker.sock is located in var run. Note, this location can vary based on the operating system and can even be manually set by the developer at runtime of the container. So it says finding the docker.sock file in a container. So I'm going to copy and paste, do an ls-la var run, then piping that into grep and sock to search for that. So let's do the same here. Okay, well, nothing came back for that. Let's go ahead and continue on. Exploring the Docker socket in a container. So I wonder if it's not on that location. Let's try something else. Maybe var, or maybe just run on root. Okay, nothing there. Let's see here. All right. Well, let's continue on and see. If we get stuck anywhere, I'll try to figure it out. Exploiting the Docker socket in a container. First, let's confirm we can execute Docker commands. You will either need to be root on the container or have the Docker group permissions as a lower privileged user. Let's break this down. All right, so breaking down the vulnerability here. We will use Docker to create a new container and mount the host file system into the new container. Then we're going to access the new container and look at the host file system. Our final command will look like this. So docker run -v /:mount -rm -it alpine chroot /mount sh, which does the following. So let's take a look here. We will need to upload a Docker image. For this room, I have provided this on the VM. It is called Alpine. The Alpine distribution is not a necessity, but it's extremely lightweight and will blend in a lot better. To avoid detection, it is best to use an image that is already present in the system. Otherwise, you will have to upload this yourself. We will use Docker run to start the new container and mount the host file system to mount in the new container. So docker run yada yada. Number 3, we will tell the container to run interactively so that we can execute commands in the container, which is the -it. Number 4, now we will use the already provided Alpine image, Alpine. 5, we will use chroot to change the root directory of the container to mount where we are mounting the files from the host operating system. 6. Now we will tell the container to run sh to gain a shell and execute commands in the container sh. You may need to Control C to cancel the exploit once or twice for this vulnerability to work, but as you can see below, we have successfully mounted the host operating system's file system into the new Alpine container. Okay, verify success. After executing the command, we should see that we have been placed into a new container. Remember, we mounted the host file system to mount, and then use root to make the containers mount become root. So let's see the contents of root by doing ls, then root. Okay. Nice. So we have some more questions here. Name the directory path which contains the docker.soc file on the container. Perform the exploit in this task on the machine. What is the value of the flag located at root flag.txt on the host operating system? So once again, pause the video, try to go through this yourself. As you saw there, when I tried to locate this docker.soc file, it wasn't there. So maybe you'll have to do some digging around. But anyway, pause the video, try it yourself, come back to the video, and then we will proceed. Hey everybody, this is WireDogSec. Just a quick reminder to subscribe to the channel and hit the notification bell. Once you hit the notification bell, be sure to set to all notifications so you know every time I post to the channel, upload a video, all that good stuff. Let's continue to grow our glorious community here. We are in the cyber trenches. We're not just reporting on it. Be sure to check out my channel as well. I have tons of videos that you can see here, over 300 videos ready for you to check out and learn something from. Be sure to review my posts. I'm frequently posting new things to my channel here, including jobs and everything related to that. Also, I have tons of playlists here that you can review, make it more convenient for you. Anyway, happy defending, happy hacking, enjoy the video. All right, let's take a look here. The first one, they're talking about that directory that's going to be in var run, even though we didn't see it. I just copy and pasted what they said above here. All right, so next one, we're going to use this here to get that flag. So highlight this and copy and paste it over here. And let's see if it works. Okay, looks like we did because it changed to the pound sign. All right, who am I? Got it. So now we need to locate the flag in root. So let's see where we are. Print working directory. All right, ls. And we need to find the root directory, which is there. So cd into root. ls, there's the flag right there. So cat flag.txt. And there we go. Pretty cool there. Now let's go ahead and check out task number 5 here. Vulnerability 3, remote code execution via exposed Docker daemon. The Docker image -tcp sockets edition. Recall how Docker uses sockets to communicate between the host operating system and containers in the previous task. Docker can also use TCP sockets to achieve this. Docker can be remotely administered, for example, using management tools such as Portainer or Jenkins to deploy containers to test their code. Yay, automation. The vulnerability. The Docker engine will listen on a port when configured to run remotely. The Docker engine is easy to make remotely accessible but difficult to do securely. The vulnerability here is Docker is remotely accessible and allows anyone to execute commands. First, we will need to enumerating, finding out if a device has Docker remotely accessible. By default, the engine will run on port 2375. We can confirm this by performing a nmap scan against our target, which is whichever IP that you have from the attack box. So I'm just going to copy and paste this out here. So basic nmap scan, versioning and everything in there. All right, so let's flip back to our attack box here, and let's go ahead and fire this off. Let me open up a new tab here and do this here. Okay. Okay, so it's running, and let's see here. Okay, let's see here. All right, it's kind of slow. Let's flip back over here. But anyway, we should get some results like this. Looks like it's open. We're going to use the curl command to start interacting with the exposed Docker daemon. Confirm that we can access the Docker daemon using curl, and then this link here. So let's go ahead and copy this, and we should get some results back like this. All right. So let's see here. It's still going slow. Let's see. We're going to paste that. All right. So we're getting information back here. Okay, so looks like we're good to go. Executing Docker commands on our target. For this, we'll need to tell our version of Docker to send the command to our target, not our own machine. We can call the -h switch to our target to test if we can run commands. We'll list the containers on the target. So docker -h TCP IP address :port, then PS. It's like so, right? So we should see something like this here, and from the attacker box. So let's go ahead and do that as such. And let's see. All right, so it looks good. So okay, let me check a couple things here. And let's go flip back over here. All right, okay, this finished. Wow, now we can see it's open. It's just running really slow for the nmap scan. But yeah, we get some information back here, so we're good to go. What now? Now that we've confirmed that we can execute Docker commands on our target, we can do all sorts of things. For example, start containers, stop containers, delete them, or export the contents of the containers for us to analyze further. It is worth recalling the commands covered in Intro to Docker. However, I've included some commands that you may wish to explore. So we have another table here, command and description. Network ls says used to list the networks of containers. We could use this to discover other applications running and pivot to them from our machine. Images list images used by containers. Data can also be exfiltrated by reverse engineering the image. Execute a command on a container. Run a container. So another question here: what port number by default does the Docker engine use? Well, we already know it runs on this port here, 2375 by default, so we're just going to plug that in as such. But we have various different commands here that we can try and exploit that vulnerability. So let's see here. Task number 6, we're going to talk about vulnerability number 4. And let's take a look here. Okay, what are namespaces? We're going to abuse namespaces, apparently. So namespaces segregate system resources such as processes, files, and memory away from other namespaces. Every process running on Linux will be assigned two things. So a namespace, a process identifier, which is a PID or PID. Namespaces are how containerization is achieved. Processes can only see the process in the same namespace. Take Docker, for example. Every new container will run as a new namespace, although the container may run multiple applications, processes. Let's prove the concept of containerization by comparing the number of processes on the host operating system in comparison to the Docker container that the host is running an Apache 2 web server. So the PS and then AUX right here, listing running processes on a normal Ubuntu system. Okay. In the first column on the left, we can see the user processes running as included. The PID. Additionally, notice the column on the very right has command or application that started the process, such as Firefox, GNOME terminal. It's important to note here that multiple applications and processes are running, specifically 320 or 320, I guess. Okay. And all right. Let's see here. So generally speaking, a Docker container will have very processes running. This is because a container is designed to do one task, i.e. just run a web server or a database. So let's go ahead and take this real quick and see something. All right, so we're on the regular Linux system here, and we have all kinds of stuff come back. Let's flip over to our Docker image here. All right. So there we go there. Okay, cool. And I'm going to clear all this out real quick. And I'm going to go back real quick and just take a look at these commands that they had mentioned. So interesting. So let's try this one and see what comes back here. Let's try this. All right, see, nice. All right, so feel free to experiment with those commands if you want to. So anyway, let's jump back to task number 6 here. And let's see here. Determining if we're in a container process. In a container processes, let's list the processes running in our Docker container using PSAUX, which we just did. It's important to note that we only have 6 processes running in this example. The difference in number of processes is usually a great indicator that we're in a container. Additionally, the first process in the snippet below has a PID of 1. This is the first process that is running. PID 1, usually init, is the ancestor parent for all future processes that are started. If for some or whatever reason this process is stopped, then all the processes are stopped too. Okay, listing running processes on a container. Okay, we already did this, so I don't think we need to go back through it again. Comparatively, we can only see that only 5 processes are running, a good indicator that we're in a container. However, as we come to discover shortly, this is not 100% indicative. There are cases where, ironically, you want the container to be able to interact directly with the host. All right, so if we get out of this here, I don't think we need to stay in root anymore. So we'll just, let's see if I still have it copied here. Let's go ahead and clear all this out and do AUX on it. Okay, so we still got a lot of stuff back here. All right, so anyway. Okay, how can we abuse namespaces, recall groups, or see groups, control groups in a previous vulnerability? We are going to be using these in another method of exploitation. This attack abuses conditions where the container will share the same namespace as the host operating system, and therefore the container can communicate with the process on the host. You might see this in cases where the container relies on a process running or needs to plug in to the host, such as the use of debugging tools. In these situations, you can expect to see the host processes in the container when listing them via PSAUX. And so here's another example, edge case, determining if a container can interact with the host processes. Okay, nice. The exploit. So this is what we are really looking for here, the meat and potatoes. For this vulnerability, we will be using nsenter, namespace enter. This command allows us to execute or start processes and place them within the same namespace as another process. In this case, we'll be abusing the fact that the container can see the sbin init process on the host, meaning that we can launch new commands such as bash on the host. Using the exploit, or use the following exploit. So nsenter --target1 mount uts ipc net bin bash, which does the following. So let's go ahead and read through this real quick. One, we use the --target switch with the value of 1 to execute our shell command that we later provide to execute in the namespace of the special system process ID to get the ultimate root. Number 2, specifying --mount. This is where we provide the mount namespace of the process that we are targeting. If no file is specified, enter the mount namespace of the target process. Okay, number 3, --uts switch allows us to share the same UTS namespace as the target process, meaning the same host name is used. This is important as mismatching host names can cause connection issues, especially with the network services. Number 4, the --ipc switch means that we enter the inter-process communication namespace of the process, which is important. This means that memory can be shared. Number 5, the --net switch means that we enter the network namespace, meaning that we can interact with network related features of the system. Example, the network interfaces. We can use this to open up a new connection, such as stable reverse shell on the host. Oh, that's interesting. 6, as we are targeting the sbin init process number 1, although it's a symbolic link, lib systemd for backwards compatibility, we are using the namespace and permissions of the systemd daemon for our new process, the shell 7. Here's where our process will be executed into the privileged namespace sh or shell. This will execute in the same namespace and therefore privileges of the kernel. Nice. You may need to Control-C to cancel the exploit once or twice for this vulnerability to work, but as you can see below, we have escaped the Docker container and can look around the host OS showing the change in host name. Okay, using the command line of the container to run commands on host, success, we will now be able to look around the host operating system in the namespace as root, meaning we have full access to anything on host. Okay, nice. Once again, perform the exploit in the task, the target machine. What is the flag located at home? TryHackMe flag. All right, so I already have it copied, and let's flip over here. Let's clear all this stuff out. All right, so let's see here. All right, so we're in the container, as you can see here. Paste, enter, and now see how it changed there. And you can do ID. Who am I? Okay, host name. There we go. Well, let's do this. It kind of got blocked there, but all right. So there we go. Framework directory, we're in root, ls, there we go, and now we need to find that flag, which is going to be in root directory, or it's going to be home this time. Okay, so we can probably just cat this and make it easy instead of just manually navigating it. Let's do cat, paste here. Oh, okay, it didn't paste correctly for some reason. Let's try this again. Okay, grab that. Okay, it won't let me grab it for some reason. Whatever. Let's go ahead and clear this out, and let's do cat. It was home. Let's see, what was it again? Home, TryHackMe, and then flag. There we go. Done. Awesome. Let's plug this in and wrap it up with the conclusion to task number 7. Phew, that was fun. In today's room, you learned about some possible misconfigurations with Docker containers, how to discover these, and ultimately exploit them. Now, you might be wondering why it is the case that containers might run with privileges that effectively bypass the security mechanism Docker introduces. Well, while it isn't a recommended practice, there are use cases where containers do need this level of interaction. For example, running Docker within Docker, or specific applications such as firewalls that need to interact with the host IP tables or perhaps attached devices. Ultimately, there is also an element of taking the quick/easy route out when trying to figure out what permissions to assign a container. That's right. Oftentimes, system admins, IT folks will press the easy button, and then that can lead to misconfigurations, i.e. open up vulnerabilities in your environment and then getting your environment pwned by an attacker. Docker, especially in recent times, does a great job of hardening. For example, you can give a container specific capabilities on an allow list basis. However, it isn't too far-fetched to think that people would just give more than necessary capabilities to get something to work without realizing the wider consequences. Yes, hurry up and get it done, right? Happens quite often in the IT world, even in today's modern day age, right? We will come on to how you can prevent these misconfigurations and vulnerabilities in the next room, container hardening. Sweet. So that'll be the next one to this, module here. Click me to finish the room. So we're done. Sweet. Hopefully y'all hung on until the end of the video, and hopefully you got something of value here. You want to help support the channel? Be sure to like, comment, share, subscribe, and hit that notification bell so you know every time I upload to the channel. Thank you all for your support. Happy hacking, happy defending. Have a nice day. I'll see you later, and stay safe in those cyber trenches. Hey everybody, this is WireDogSec. Just a quick reminder to subscribe to the channel and hit the notification bell. Once you hit the notification bell, be sure to set to all notifications so you know every time I post to the channel, upload a video, all that good stuff. Let's continue to grow our glorious community here. We are in the cyber trenches. We're not just reporting on it. Be sure to check out my channel as well. I have tons of videos. You can see here over 300 videos ready for you to check out and learn something from. Be sure to review my posts. I'm frequently posting new things to my channel here, including jobs and everything related to that. Also, I have tons of playlists here that you can review, make it more convenient for you. Anyway, happy defending, happy hacking, enjoy the video. Hey everybody, welcome back to my channel. This is WireDogSec, Back with another video for you guys. Today's video, we are in TryHackMe. This is the container hardening room. Learn how to implement the mechanisms designed to secure your Docker containers. So task number 1, introduction. So far, this module has taught you the basics of Docker and the potential vulnerabilities associated with containers. This room will teach you the various ways of securing your containers. Learning objectives: secure the Docker daemon to prevent unauthorized interaction, correctly assign privileges, capabilities to containers, prevent faulty or malicious containers from exhausting a system, utilize security features such as seccomp and app armor to define how your containers will behave with the operating system, practice good hygiene by reviewing Docker images for vulnerabilities, implement frameworks and tooling that reviews your code for vulnerabilities. Quite a few items here that we're going to discuss and learn about. Prerequisites. In order for you to complete this room, it is essential that you are familiar with the various components of Docker. I highly recommend completing the intro to Docker room before proceeding, or check out my previously created videos about Docker and containers in general. Just search my channel and you will find them. Or if you're watching the full module for this, you should already progress through those videos. Read the above before proceeding to the next task. So we've done that. And also, if you want to, you can scroll all the way down here to the practical side of things and go ahead and start up that VM and whichever else is down here so that you'll be ready to go. But we're going to go ahead and read through everything here, and then we'll start up as we get closer to that particular task. But as usual, if you want to help support the channel, if you're enjoying the content, be sure to like, comment, share, subscribe, and hit that notification bell so you know every time I upload to the channel. Without further delay, let's go ahead and dive into it. Task 2, protecting the Docker daemon. You may recall from the Container Vulnerabilities room that the Docker daemon is responsible for processing requests such as managing containers and pulling or uploading images to a Docker registry. Docker can be managed remotely and is often done in CI, continuous integration, and CD, continuous development pipelines. For example, pushing and running new code in a container on another host to check for errors. If an attacker can interact with the Docker daemon, they can interact with the containers and images. For example, they launch their own malicious containers or gain access to containers running applications with sensitive information, such as databases. The Docker daemon is not exposed to the network by default. It must be manually configured. However, exposing the Docker daemon is a common practice, especially in cloud environments such as CI/CD pipelines, which is what we just clarified up here, okay? So let's go and continue on. Implementing secure communication and authentication methods such as those listed below are extremely important in preventing unauthorized access to the Docker daemon. SSH. Developers can interact with other devices running Docker using SSH authentication. To do so, Docker uses contexts which can be thought of as profiles. These profiles allow developers to save and swap between configurations for other devices. For example, a developer may have one context for a device with Docker for development and another context for a device with Docker for production. Note, you must have SSH access to the remote device, and your user account on the remote device must have permission to execute Docker commands. As the developer, you will need to create the Docker context on your device. Please see the code snippet below to create a context within Docker. So let's take a look at this, creating a new Docker context. All right, so we have Docker context create, and then we have -- Docker host equals SSH, and then my user at remote host, description, development environment environment host, successfully created context, development environment host, or just development environment host. Once this has been completed, you can switch to this context where all Docker related commands will now be executed on the remote host. So it says, using our newly created Docker context use development environment host. Current context is now development environment host. So it sounds pretty straightforward. To exit this context and, for example, use your own Docker engine, you can revert to default via Docker context use default. Note, this is not entirely secure. For example, a weak SSH password can lead to an attacker being able to authenticate. As with anything, right? Weak credentials, you can get pwned. A strong password hygiene is strongly recommended. Some tips for a strong password have been included below. So it says a high amount of characters, has examples of that, 12 through 22 plus. Special characters such as exclamation mark, @ symbol, the hash sign or pound sign, and the $sign. Capital letters and numbers placed sporadically throughout. Examples, super secret password, and it has different characters in there, substitution characters, things of that nature. So we get the point. You should know how to create a secure password or passphrase by now. And also be sure to use a password manager to store these credentials so you don't have to remember everything. And also password managers can help you create strong passwords, right? Let's continue on. Docker contexts allow you to interact with Docker daemon directly over SSH, which is a secure and encrypted way of communication. OS encryption. The Docker daemon can also be interacted with HTTPS. This is useful if, for example, a web service or application is going to interact with Docker on a remote device. To do this securely, we can take advantage of the cryptographic protocol TLS to encrypt the data sent between the devices. When configured in TLS mode, Docker will only accept remote commands from devices that have been signed against the device you wish to execute Docker commands remotely. Note, creating and managing TLS certificates is out of scope for this room, as you will often need to consider factors such as expiry date and strength of encryption for your environment. Once you have created your certificates, you can tell Docker to run in TLS mode with the generated certificate on the host server that you are issuing the commands from. So here's an example here, running Docker in TLS mode, right? So it's docker d --TLS verify --TLS ca cert equals my ca cert.pym. Then has --cert or TLS cert, my server, and you can see the rest there. Next one, telling Docker local to authenticate using TLS. So here's another example here, docker --TLS verify, and you can see the rest here. Note, it is important to remember that this is not guaranteed to be secure. For example, anyone with a valid certificate and private key can be a trusted device. I have explained the arguments used in generating a TLS certificate and the key in the below table. So let's take a look. So argument and description here. --TLS ca cert. This argument specifies the certificate of the certificate authority. A certificate authority is a trusted entity that issues the certificates used to identify devices, --TLS cert. This argument specifies the certificate that is used to identify the device, and then the --TLS key. This argument specifies the private key that is used to decrypt the communication sent to the device here. So seems pretty straightforward, right? Okay, so we have some questions here. What would the command be if you wanted to create a Docker profile? And then what would the command be if you wanted to switch to a Docker profile? So, okay, so create and switch, and that was discussed earlier up here, right? So you would use Docker context create for that first one. So let's go ahead and copy that and paste it below here. Okay, and then now we need to go to the switch one, which is the one just below it. So Docker context use if you want to switch between those. Okay, so let's go ahead and plug that in as our answer, and then we will continue on here to task number 3. And for some reason, these tasks don't automatically close as you proceed. Kind of annoying. Task number 3, implementing control groups. Control groups, also known as C groups, are a feature of the Linux kernel that facilitates restricting and prioritizing the number of systems resources a process can utilize. For example, a process such as an application can be restricted to only use a certain amount of RAM or processing power, or given priority over other processes. This often improves system stability and allows administrators to track system resource use better. In the context of Docker, implementing C groups helps achieve isolation and stability, because C groups can be used to determine the number of or prioritize resources a container uses. This helps prevent faulty or malicious containers from exhausting a system. Of course, the best mechanism is preventing this from happening, but preventing a container from bringing down a whole system is an excellent second line of defense. This behavior is not enabled by default on Docker and must be enabled per container when starting the container. These switches used to specify the limit of resources a container can use have been provided in the table below. Okay, so let's take a look at this table. We have type, a resource, argument, and example. CPU, --CPUs, and core count. And then his example, Docker run -IT, -CPUs equals 1, my container. Next one, memory, --memory, NK, MG for kilobytes, megabytes, or gigabytes. Docker run -IT, -memory equals 20 M. And then my container. You can also update this setting once the container is running. To do so, use the Docker update command, the new memory value in the container name. For example, Docker update -memory equals 40 M, my container. Useful there. You can use the Docker inspect container name command to view information about a container, including the resource limit set. If a resource limit is set to 0, this means that no resource limits have been set. Using Docker inspect to list the resource limits set for containers. So here's an example of that. So Docker inspect my container, and then it dropped off that information or displayed the information back to you. So we have memory, CPU quota, etc., etc. So all those resources listed there, right? Let's see here. Docker uses namespaces to create isolated environments. For example, namespaces are a way of performing different actions without affecting other processes. Think of these as rooms in an office. Each room serves its own individual purpose. What happens in a room in this office will not affect what happens in another office. These namespaces provide security by isolating processes from one another. Interesting. Question time. What argument would you provide when running a Docker container to enforce how many CPU cores the container can utilize? Okay, so let's see here. It would be this here, Docker run IT, then CPU use equals whatever, right? Okay, so we just need the argument, which is going to be this dash CPUs. So let's just go ahead and grab this and plug that in as our answer there. Okay, if I can highlight correctly. There we go. All right, next one here. What would the command be if we wanted to inspect a Docker container named Apache? And we can see that here. So Docker inspect and then Apache for that name of the container, right? So let's go ahead and plug that in. Then Apache. And we should be done. Awesome. So now let's proceed to task number 4 here. Hey everybody, this is WireDogSec. Just a quick reminder to subscribe to the channel and hit the notification bell. Once you hit the notification bell, be sure to set to all notifications so you know every time I post to the channel, upload a video, all that good stuff. Let's continue to grow our glorious community here. We are in the cyber trenches. We're not just reporting on it. Be sure to check out my channel as well. I have tons of videos that you can see here, over 300 videos ready for you to check out and learn something from. Be sure to review my posts. I'm frequently posting new things to my channel here, including jobs and everything related to that. Also, I have tons of playlists here that you can review, make it more convenient for you. Anyway, happy defending, happy hacking, enjoy the video. Task 4, preventing overprivileged containers. First, we need to understand what privileged containers are in this context. Privileged containers are containers that have unchecked access to the host. The entire point of containerization is to isolate a container from the host. By running Docker containers in privileged mode, the normal security mechanisms to isolate a container from the host are bypassed. While privileged containers can have legitimate uses, for example, running Docker in Docker, a container within a container, or for debugging purposes, they are extremely dangerous. When running a Docker container in privileged mode, Docker will assign all possible capabilities to the container, meaning the container can do and access anything on the host, such as file systems. A diagram demonstrating the difference of container mode privileges. So container 1, container 2 are normal mode. So you have application 1, application 2, environment, and they go to the Docker engine here. Whereas container 3 is in privilege mode. So application 3, environment, goes straight to the computer operating system, the host. Okay. What are capabilities? I hear you ask. Capabilities are a security feature of Linux that determines what processes can and cannot do on a granular level. Traditionally, processes can either have full root privileges or no privileges at all, which can be dangerous as we may not want to allow a process to have full root privileges, as it means it can have unrestricted access to the system. Capabilities allow us to fine-tune what privileges a process has. I have placed some standard capabilities in the table below. What privileges they translate to and where they may be used. So take a look at this table here. We have capability, description, and use case. So cap net bind service. This capability allows services to bind to ports, specifically those under 1024, which usually requires root privileges, and then the use case allowing a web server to bind on port 80 without root access. Next one is cap sysadmin. This capability provides a variety of administrative privileges, including being able to mount or unmount file systems, changing network settings, performing system reboots, shutdowns, and more. You may find this capability in a process that automates administrative tasks, for example, modifying a user or starting or stopping a service. The last one here, cap sys resource. This capability allows a process to modify the maximum limit of resources available. For example, a process can use more memory or bandwidth This capability can control the number of resources a process can consume on a granular level. This can be either increasing the amount of resources or reducing the amount of resources. To summarize, privileged containers are containers assigned full privileges. Examples, full root access. Attackers can escape a container using this method. If you would like homework, this process has been demonstrated in the Containers Vulnerabilities room, or check out my channel for that video. It's recommended assigning capabilities to containers individually rather than running containers within the -- privileged flag, which will assign all capabilities. For example, you can assign the net bind service capability to a container running a web server on port 80 by including the -- cap -add equals net bind service when running the container. So instead of pressing the easy button, you can use this alternative method, which is more secure from what we just read here, right? Let's take another look at an example here. Assigning the net bind service capability to a container. So you have docker run -it -rm -cape or cap drop equals all cap add net bind service my web server. Finally, the command cap sh -print can be used to determine what capabilities are assigned to a process. Interesting there. Using cap sh to list the capabilities currently assigned. So here it is, cap sh -print, and it lists all those capabilities as we can see here. So it looks like there's quite a few of them listed down here. It is important to frequently review what capabilities are assigned to a container. When a container is privileged, it shares the same namespace as the host, meaning resources on the host can be accessed by the container, breaking the isolated environment. Okay, so now we know the easy mode, right? And we have another way of doing it, which is a more specific mode, as we can see here, right? So that's good information there. And then if we want to check it, we can just use this cap sh -print to list that out. So if you were like an administrator or IT person working on this, if you want to check what's assigned there, use this command here. And if you're an attacker, I guess you can use the same thing as like reconnaissance to see what it all has listed there. Let's take a look at these questions. What is the name of the capability that allows services to bind to ports, specifically those under 1024? Well, we just saw that up here. That's that net one, right? The cap net bind service is going to be that one here. So let's plug that in as our answer. All right. What argument would we provide when starting a Docker container to add a capability? All right. So if we want to add a capability, it should be this here. Just -- add. So let's go ahead and put that in there as our answer there. Next one, finally, what command with argument would we use to print the capabilities assigned to a process? So that's going to be that the cap sh -print, as we just saw up above here. Okay. And task number 5, seccomp and AppArmor 101. Seccomp is an important security feature of Linux that restricts the actions a program can and cannot do. To explain, picture a security guard at the entrance of an office. The security guard is responsible for making sure that only authorized people are allowed into the building and that they do what they are supposed to do. In this scenario, seccomp is the security guard. Seccomp allows you to create and enforce a list of rules of what actions, so system calls, the application can make. For example, allowing the application to make a system call to read a file, but not allowing it to make a system call to open a new network connection, such as a reverse shell. These profiles are helpful because they reduce attackers' ability to execute malicious commands whilst maintaining the application's functionality. For example, a seccomp profile for a web server may look like the following here. So we have default action, scmp, act allow, and then here's a list of architectures, and then here's the syscalls, right? So names here says read, write, exit group, etc., etc., etc. All right. So it's kind of like, I guess, similar to like setting ACLs, access control list type of thing, right? Setting those specific, I guess, permissions that it's allowed to do. This seccomp profile allows files to be read and written to, allows a network socket to be created, but does not allow execution. For example, exec ve, okay? As we can see here, it looks like that. All right, so yeah, so at the end here, action is right there. Okay. So there we go. For that one, to create a seccomp profile, you can simply create a profile using your favorite text editor. This room will use Nano. An example seccomp profile.json has been provided below. This profile will allow reading and writing access to files, but no network connection. So let's take a look here. At default action, scmp act allow. There's architecture. Here's the list of syscalls here. Okay. And it says that no network connection. So you can see that the SMP act error no. So socket connect, can't do that, can't do bind, listen, etc., etc. So I think we get the gist of it. And then things that it's allowed to do, read and write. All right. Without our sec profile, or with our sec profile now created, we can apply it to our container at runtime by using the --security.--opt setcomp flag with the location of the setcomp profile. For example, applying our setcomp profile when running a container. Again, docker run -rm-it -security-opt, and then setcomp equals the location of that particular profile, right? Profile.json, and then my container is where you're going to apply that to. Docker already applies a default setcomp profile at runtime. However, this may not be suitable for your specific use case, especially if you wish to harden the container further while maintaining functionality. You can learn more about using setcomp with Docker here, so go ahead and check that out as extra homework here and to expand your knowledge and skill set. Okay. AppArmor. AppArmor is a similar security feature in Linux because it prevents applications from performing unauthorized actions. However, it works differently from setcomp because it is not included in the application but in the operating system. This mechanism is a mandatory access control, or MAC, system that determines the actions a process can execute based on a set of rules at the operating system level. To use AppArmor, we first need to ensure that it's installed on our system. So it says checking if AppArmor is installed or not. Sudo AA-status, AppArmor module is loaded, 34 profiles are loaded. With the output AppArmor modules loaded, we can confirm that AppArmor is installed and enabled. To apply an AppArmor profile to our container, we need to do the following. So create an AppArmor profile, load the profile into AppArmor, and then run our container with the new profile. First, let's create our AppArmor profile. You can use your favorite text editor for this. Note that there are tools out there that can help generate AppArmor profiles based on your Docker file. However, this is out of scope for this room and can be unreliable. Provided below is an example of AppArmor profile.json for an Apache web server that can read files located in var www etc apache2 mime.types and run apache2. Read and write to var log apache2, bind to a TCP socket for port 80, but not other ports or protocols such as UDP. Cannot read from the directories such as bin, lib, or user. All right, so here's an example of that. User sbin, HTTP, capability set GID, capability set UID. All right, and then we have var www, and you can see the rest here. So go ahead and just review that on your own. Okay, and it says system logging, allow CGI execution, deny access to everything else. Good information there. Now that we have created the AppArmor profile, we will need to import this into the AppArmor program to be recognized. So importing our AppArmor profile into AppArmor. This is how you would do it. Sudo AppArmor _parser -r -W home semantic container1 AppArmor and then profile.json. With our AppArmor profile now imported, we can apply it to our container at runtime by using the --security-opt AppArmor flag with the location of the AppArmor profile. For example, so this is applying it. So docker run -rm-it -security-opt AppArmor equals, and then the location of that profile, right? And then the name of your container that you're going to be targeting. Just like setcomp, Docker already applies a default AppArmor profile at runtime. However, this may not be suitable for your specific use case, especially if you wish to harden the container further while maintaining functionality. You can learn more about using AppArmor with Docker here, so go ahead and check that out as well to expand your knowledge and skill set in that area. What's the difference? Well, to put it briefly, AppArmor determines what resources an application can access, examples, CPU, RAM, network interface, file system, etc., and what actions it can take on those resources. Setcomp is within the program itself, which restricts what system calls the process can make, examples, what parts of the CPU and operating system functions. It's important to note that it is not a one or the other case. Setcomp and AppArmor can be combined to create layers of security for a container. Okay, so it looks like you'll have to utilize both of these if you want to lock these down or harden them as much as you can, right? Okay, so let's take a look at these questions. If we want to enforce the container to only be able to read files located in home TryHackMe. What type of profile would we use? SecComp or App Armor? See here, for a container to only read files, I believe. And this is going to be App Armor, as we can see up here under this, to put it briefly, okay? So home, TryHackMe, that's going to be the targeting the file system, right? So you're going to use App Armor for that one. Next one says if we wanted to disallow the container from a system call, such as clock, adjust time, what type of profile will we use? SecComp or App Armor? Well, you can set up here, we're just talking about syscalls, right? System calls to the process, that's going to be SecComp. And last one here is finally, what command would we use if we wanted to list the status of App Armor? And if we scroll back up here, it talks about it right here. This AA status, App Armor modules loaded, 34 profiles are loaded, etc., etc. So we're done with that one, and let's proceed with the next one here, which is task number 6, reviewing Docker images. Reviewing Docker images is an extremely important habit to practice. You would be wary of running unknown code on your device, so why would you consider running it in a production environment? Unfortunately, there are numerous examples of malicious Docker images causing havoc. For instance, in 2020, Paul Alto discovered crypto mining Docker images that were pulled and presumably ran over 2 million times. Wow. Images on Docker Hub often come with Dockerfiles attached to the repository. For example, the Docker Hub displays the layers, therefore the commands executed for the Docker file. And here's an image of what that looks like here. All right. The image above, we can see various layers of the Docker image on Docker Hub. These layers are the steps that are executed during the building process of the image. Additionally, open source code repositories for images on the Docker Hub will often be included, allowing you to review the entire Docker file. So that's nifty there. Here's an example of that. It looks like here. Okay. The image above, we can see the code for the Docker file. This allows us to audit the code and understand precisely what actions are being executed in the container. By analyzing the code, we can check for vulnerabilities and malicious actions. Tools such as Dive allow you to reverse engineer Docker images by inspecting what is executed and changed at each layer of the image during the build process. Okay, and the image is not loading there, but if you want to check out Dive, go ahead and click on this link here and it'll take you to that GitHub page, it looks like here. Yes. Okay, I understand how I can review both Docker files and Docker images. Complete me to proceed to the next task. Let's do that. And task number 7, compliance and benchmarking. First off, let's scroll down to the practical and just start this machine up here so we don't have to wait for anything. Okay. Task number 7. Compliance and benchmarking play vital roles in securing assets, let alone containers. Let us begin by explaining compliance. Compliance is the process of following regulations and standards such as the NIST SP 800-190, a set of standards from the National Institute of Standards and Technology that gives guidance and best practices on container security. So we have another table here. Compliance network, description, and URL. NIST SP 800-190, the framework that outlines the potential security concerns associated with containers and provides recommendations for addressing these concerns. And here's a link to that if you want to check that out, which I recommend going and doing so. ISO 27001. This framework is an international standard for information security. The standard guides implementing, maintaining, and improving an information security management system. So here's a link to that if you want to check that out. Please note that you may have to adhere to additional frameworks relevant to your industry. For example, financial or medical regulations exist in all industries. For example, in the medical field, the HIPAA for handling medical data. Benchmarking, on the other hand, is a process used to see how well an organization is adhering to best practices. Benchmarking allows an organization to see where they are following best practices well and where further improvements are needed. So here is the table for that. So benchmarking tool, description, and URL. CIS, Docker, benchmark. CIS is well known out there. They have a ton of other benchmarks out there. You name it, they probably have a benchmark for it. Description, this tool can assess a container's compliance with the CIS Docker benchmark. Here's a link to that. OpenSCAP. This tool can assess a container's compliance with multiple frameworks, including CIS Docker benchmark, NIST SP 800-190, and more. Here's a link to that. Docker Scout. This tool is a cloud-based service provided by Docker itself that scans Docker images and libraries for vulnerabilities. This tool lists the vulnerabilities present and provides steps to resolve these. And next one is Encore, I guess. This tool can assess a container's compliance with multiple frameworks, including CIS, Docker, Benchmark, and then NIST SP 800-190 and more, and then Gripe. This tool is a modern and fast vulnerability scanner for Docker images. So a lot of different tools that you can use to help you secure these images, right? An example of using the Docker Scout tool to analyze a Docker image has been provided in the terminal below. Please note this will need to be installed beforehand. You can read the Docker Scout documentation to learn more. All right. So we can take a look at this real quick, using Docker Scout to scan our Nginx image for vulnerability. So Docker Scout, CVES, local, and then the location of that, SBOM of image already cached, 215 packages. Index detected 22 vulnerable packages with a total of 45 vulnerabilities. Overview, analyze image, and you can see all kinds of looks like useful information that you can utilize to your advantage. Lists out those CVEs that appear to affect that particular instance, right? So a lot of good information there. Okay, so question time. What is the name of the framework published by the National Institute of Standards and Technology? For this answer, be sure to include the full name. So that's going to be that long name right here. So this NIST SP 890. And I believe SP stands for Special Publication, if I'm not mistaken. So let's plug that in. Oops, what happened here? Okay, and if we didn't copy correctly, 800-190. So let's try that again. All right. What is the name of the analysis tool provided by Docker? And that's in this table here. So let's see here. That's not that one. Yes, so Docker Scout is going to be our answer for this one. Okay. Docker and then Scout. Got it. Okay, so task number 8 here, practical. Deploy the machine attached to this task by pressing the green start button, which you've already done. Show split view if it's not showing up, okay? Your task is to use the Gripe vulnerability scanner on the machine to analyze some Docker images. Gripe can be used to analyze Docker images and container file systems. You can refer to the table below as a cheat sheet to answer the questions in this task. So the table, example, description, and the command. Scanning a Docker image. Scan a Docker image for vulnerabilities. So Gripe image name -- scope all - layers. Scanning an exported container file system. Scan an exported container file system. Example from Docker image save. So Gripe then path to image.tar. Please note that for this room, you can safely ignore the unable to check for vulnerability database update warning messages. Okay. All right. So we have a few questions here to answer. So go ahead and pause the video, try to answer them yourself, and then come back to the video, and then we will proceed further. All right. Welcome back. Hopefully you're able to find these answers. We're going to skip around a little bit here. We're going to take a look at the second one. Use Gripe to analyze the struts2 image. What is the name of the library marked as critical? So let's flip over here. Now to do this, you do this Gripe and then struts2 and then -- scope all - layers. This takes a few minutes to run, which is why I'm skipping around here. But if you ran it correctly, you should get all this information back to you. Now, when you go down and scroll all the way to the bottom here, and you see the one marked as critical, and this is going to be struts2 - core for that one. Okay. So struts2 - core. -core. All right. Now for this one here, this one's pretty easy to run. I'm just going to clear all this out and up arrow to get it. Docker ps. Okay. So you have container ID, image, command, created, status, ports, names. All right. We're looking for the name of it, and it's going to be this couchdb. Okay. So that's going to be the answer for that one. And this last one here, use Gripe to analyze the exported container file system located at root container.tar. What is the severity for CVE-2023 45853 rated as? So doing ls here, you can see the file right there. All right, let's go ahead and clear this out, and I'm going to just paste this in here. So Gripe root container.tar. Okay, so once this gets done parsing, it'll display all kinds of information related to CVs and such, I believe. And then we should be able to locate that particular one inside every once this finishes running. I don't think this should take very long. If any way I can just fast forward the video if it's going to take forever. But I wonder if we can just combine this with like grep to look for this specific CVE, right? So let's flip back over here. Okay, so that didn't take long at all. And all the way here at the bottom, CVE 2023 45853, and it's rated as a critical. So we're going to plug that in as our answer. All right, first off, let's go ahead and clear this out. Now I'm just going to test this out real quick for grep. I'm going to pipe this into grep. Okay, and then we're going to just paste that in there, this particular CVE here. Okay, and let's see what it does here. It should just display that one, but I want to see if it actually does it or if it displays everything as we just saw there. And hopefully this doesn't take too long to run. Wait, so there's several different tools that was referenced in the previous task there, but if you want to learn how to use this particular gripe thing, there's the examples up here in this table. All right, so let's flip back over, see if it's done, and there we go. So yes, using grep, we can just limit it down to that specific CV that you're looking for. Okay, and we are done with this here. Let's plug this in and wrap up this video. All right, we are done. Awesome. So if you enjoyed the content, enjoying the video, we have all kinds of information going on this channel here. And you want to help support the channel, be sure to like, comment, share, subscribe, and hit that notification bell so you know every time I upload to the channel. Thank you all for taking the time to watch my video. Happy hacking, happy defending. I'll see you later. Have a good one. Stay safe in those cyber trenches.